All right, let's do a sound check. Can people online confirm that they can hear me, please? Just put something in the chat or whatever.
Yes.
Okay, yeah, sounds good. Thank you. Let's give it a little longer because people are still joining online, apparently. And then we'll get started in, let's say, 1 or 2 minutes. Okay, let's get started. So welcome to the session on Python on GPUs. This is a VSC training, so Flemish Supercomputing Center, but also a EuroCC training. So the Belgian National Competence Center is also co-organizer of this training. Usually I have a slide with QR codes and so on. So let's skip that this time, because actually for this particular session I don't have any slides. So it's pure Jupyter Notebooks, which is slightly different approach than what I did in the past, but I think it's a bit more interactive and a bit more appealing at times. What I will do is paste the link to the page which you just saw in the chat, and that will lead you to this web page that gives you a bit of an overview of what we plan to do today, but also more importantly it has a link to the repository, and that repository contains all the source code, all the notebooks I'm going to use during this training. So as usual, it's available. This is the repository. So you can access the repository, you can fork it, you can clone it, whatever you like. No problem there. It's all in the public domain, so but it's licensed. So if you use anything, you should acknowledge me. Anyway. Let's get started. So basically, there are quite a number of ways to use GPUs. And of course, the more classical approach would be to program in some C dialect, C++ dialect, such as CUDA for NVIDIA or HIP for AMD. And yeah, that works, but of course, it's a lot of work. And typically, it means that you, besides knowing these particular dialects, also need to be quite familiar with C++, which may or may not be an obstacle. So the good news is that for Python, there are quite a number of libraries that allow you to use the power of GPUs without specifically needing to know how to program them in CUDA/HIP, whatever. So basically, that can be quite a bit of help there. So that's one way to use them. The other way to use them, of course, is to use libraries that just under the hood run code on GPUs. That's of course quite easy, and that's of course well, the simplest thing you can do. So basically, we will see a number of things here. Let's go to the source code directory. Yeah, let me maybe do a little bit of motivation first. Yeah, probably I don't need to convince you that GPUs are an integral part of the HPC ecosystem today, and that they can give you significant extra performance with respect to your typical CPU, which does not mean that a CPU, especially since you typically have two in HPC systems, is not a powerful compute device. So basically, if your application is well suited to run on a GPU, you will gain substantial performance benefits, but they might be perhaps a bit less than you might expect. So back in the days, you often saw publications that claimed, okay, I have my old code, now I rewrote it for GPU, and all of a sudden my code runs 100 times faster, 200 times faster, and so on. Okay, that typically means that that old code which ran on a CPU was not well optimized. So the screen isn't clear. Okay. What do you mean by the screen isn't clear? What you're seeing right now is just a terminal and part of the chat. That's what you ought to see. Okay. So I'm guessing it's a local problem. Yeah, it must be a local problem. Yeah, sorry about that, internet connections and so on. But I'm guessing it's not a general thing and something I can't do anything about on my side, I'm afraid. Yeah, probably something like that. Okay. So basically, if you hear claims that the GPU is 1,000,000 times faster than a CPU, then no, that's typically not the case. You can gain up to a factor of 10 realistically, especially with modern GPUs. But yeah, much more than that is typically a little bit of an exaggeration. There are, of course, exceptions. Some codes really run very fast on GPUs, but in general, if you get a factor of 5 to 10, you're quite happy. And of course, a factor of 5 to 10 is quite a lot, so it's definitely worth the effort. But just to kind of set your expectations, don't go wild on that, because basically, yeah, typically claims are slightly overblown, to say the least. Okay, why do they work so well? Why are GPUs performing computations pretty fast? There's several reasons for that. The first reason is massive parallelism. So basically, if you look at the typical CPU, you will have something like, at the moment, depending on what you buy, 36 cores, 48 cores, even 128 cores per CPU, very modern CPUs. So basically, that's the level of parallelism you can expect. Multiply that by 2 if we're talking in compute node in a typical HPC cluster. So we're talking a maximum of, say, 256 threads on an HPC node. So that's about the maximum you can get. So that number of cores, of compute units in a GPU is much larger. That's of the order of thousands, so 3,000 to 5,000, depending on which particular GPU you're using. So that is already a reason why you should expect things to be faster on GPUs. Easy. Another reason why GPU computations may be significantly faster is memory bandwidth. So the memory bandwidth so the memory bandwidth in GPUs is typically also a lot larger than on CPUs. So basically that means that you can get your data a lot faster from the dedicated memory on your GPU card to your actual compute units, to your cores, then you can do that on CPU. So that bandwidth is a lot bigger. So that also helps because many scientific codes are in fact memory bound. So if you can move data faster, if you can move data more efficiently, that means that typically you will get a better performance. So that's the second reason. The third reason is that GPUs, especially modern GPUs, A100, H100, and so on, they typically contain specialized hardware that really helps in scientific computing. So basically, tensor cores, tensor units, they will typically help in doing simple stuff like matrix multiplications and so on. And of course, our scientific codes are typically matrix vector operations, matrix operations, and so on. So if there is specialized hardware to accelerate that, then of course the GPU also has an edge for that type of workloads. So basically that means that you have 3 factors that each contribute to ensuring that you get interesting performance numbers on GPUs. So yeah, that's basically the reason why this is a good idea. Now, one of the things that people did, of course, was they took old code, and of course you never touch old code because then it breaks, but to port them to GPU, they didn't have a choice. So basically they retaught their code and they started optimizing it for GPU. If you do the same thing on CPU, you'll also see a performance increase. So that's why you get these inflated numbers, because people typically rewrite the code from scratch, rethink, redesign the code in order to take maximum advantage of the GPU architecture, and they don't have the time or don't want to be bothered to do that on CPU. So that's a reason for the inflated figures which you sometimes see being claimed. Is that a bad thing? No, because at least someone looked at the code and optimized it. Even if it's only at least someone thought about the code, which is always a good thing. Okay, so let's go into the Python thing. So I'm here on the command line, and this is basically the repository, which you also have access to. I'll put a link again in the chat because I don't know if anyone joined a little later, but if so, you don't see the history of the chat and you don't see the link. So I'll paste it again just to make sure that everyone can access that. Okay, so there are a number of directories here, and basically it's a little bit in order of, let's say, difficulty in a sense. So maybe let's start with NUMA. So those of you who actually did the Python for HPC training of last Wednesday and Monday, they know about NumPy. So NumPy is a framework, let's say, that allows you to easily optimize Python code. The idea is you simply decorate functions, and as a result of that, the code is taken and the Python code and translated into C++. The C++ code is compiled, it's put into shared object, and rather than running your Python code under the hood, you run compiled C++ code. And that, of course, significantly speeds up the computations. So that's a very nice framework. It's reasonably simple, just decorating functions. In the very simplest case, it's just decorate with @JIT, and you're done. If you want to go a little bit further, you give extra information about the signature of the function so that the compiler has an easier task in generating code to bind your C++ code to that generated C++ code. Okay, but one of the things that I mentioned at the end of that particular section was that there were a few things not covered, and one of those was how to use NumPy on GPUs. So let's perhaps have a look and see how that works. I'm going to make sure that this happens. Okay, now I'm just curious to see what happens. Okay, so yeah, that is. I was curious to see whether this happened because I have that problem with another environment and I updated that, so I didn't know. But basically, I have the same problem here. So apparently, it's the WSL thing which changed, which is a bit annoying, but never mind. Okay, now at least I know. So. And that is already a good thing. Okay, so let's go here and let's increase the size of this window a little bit, because otherwise I'm not going to be able to read this. Okay, so NumPy. All right, so quite a lot of imports, as you can see. The usual suspects like math, like matplotlib, like itertools, and so on. So that's all standard Python stuff you're familiar with, no problem. It gets interesting when we start importing from NumPy. So basically, you might remember JIT and NJIT. So those were the decorators for, and Vectorize as well. Those were the decorators which we already talked about in Python for HPC. But the new one is the CUDA thing. Specifically from CUDA, we want some random number generator, and basically that's the thing which we're loading in the second line. Maybe let me display line numbers. That might help. Then I can talk about line number and such. Okay, why doesn't this work? Okay. Weird. I ought to be able to display line numbers, but it doesn't seem to work for some reason. Okay. We also need NumPy, and we use random. Okay. So we define a couple of functions, and just to make sure that we can compare without messing things up, I have the same function several times. So I do a decoration on a different function so that I can still compare them properly. So as you can see, the function Gaussian pure, it doesn't do much. It takes 3 arguments, x, mu, and sigma. And first, it checks whether x is a float. Basically, then it can do the math very simply. So essentially what we're doing is we're raising it to the power 2 after subtracting mu, which is the mean. We divide by sigma and so on. So basically, this is evaluating the Gaussian function. And in this case, if x is something we can iterate over, then essentially we want a list of results. And this is really pure Python, so I'm using list and map and so on. Okay. The mu and the sigma thing. Okay, let me do that in a separate notebook, because I don't want to mess up this one. So basically, if you want some Greek letter or some special symbol in a Jupyter notebook, what you can do is you do backslash and you type, for instance, sigma, and then you hit the tab key. And as you can see, it then offers the suggestion to convert that to a letter sigma. So basically, now I can work with the sigma, for instance, 3 times, again, sigma tab, and so on. A caveat this, you can do that, but what I would strongly discourage is to use special characters like this in names of functions and such. By which I mean everything that is user-facing. If you're developing a library, don't do this kind of thing, because you will really annoy people. Because first, many people don't know the trick in Jupyter Notebooks, and secondly, if you're not using Jupyter Notebooks, you can still use these Greek letters, but then you have to know how to type them in your favorite editor. And that's, of course, that depends on the editor you're using, and then you're really going to piss off people. If I'm just programming in Python, I typically use NeoVim. And really, if I have to look up how I get a sigma type there, you're not going to make me happy. So use this with caution, let's put it that way. I typically like it for teaching purposes, because then basically you're a bit closer in notation to your typical physics or mathematics or whatever. But apart from that, be a bit careful about it. Also, of course, it's more work to type. So, okay. Did I actually? I don't think I executed this. So let's do that. Okay. Yeah, one thing I also need to mention. So of course, all of this works, but it only works because of this file here, environment.yaml, which basically is a definition for a Conda or a Mamba environment. So all the libraries which you would need, probably except for Rapids, is actually in this file. So it's very easy to instantiate an environment which should, in theory at least, be able to run this. Okay, let me also increase the font size here a little bit. Okay. All right, so that's our simple code. And of course, what we want to do is, at the end of the day, just feed it some NumPy array. So basically, I'm setting some values. And note that I'm pretty explicit here. because I actually want to do this computation in 32 bits. Okay, the reason for that is that I would prefer to compare apples to apples, because mostly I developed this kind of training material on my laptop, which has a consumer level graphics card, an RTX 3060 something, and basically doing double precision on that is not necessarily your best idea. Also, typically, depending on your application, you're likely to use single precision anyway. Of course, GPGPUs, dedicated GPGPUs such as P100, V100, A100, H100, whatever, they will support and will run double precision computations, no problem. But of course, your single precision computations will be faster. They will be significantly faster. So if you don't need double precision for your computations, don't use it, because it's going to comparatively slow you down. Another reason, of course, is that a double precision number is 64-bit, 8 bytes. Single precision is half of that, 32 bits, 4 bytes. So basically that means that your effective memory capacity can hold twice as many floating point numbers than it can, well, sorry, single precision floating point numbers than it can double precision floating point numbers. Since memory on GPUs is really at a premium, you do want to take that into account, because basically the more data you need to move from the host memory to the GPU and back, the less happy you're going to be, because that's always going to be your bottleneck, the PCI bus, which basically connects your GPU to your CPU. And that is really a bottleneck due to, on the one hand, latency. So basically it takes a while before actually anything happens if you try to transfer something across the PCI Express. And also the bandwidth is not really very high. So, of course, things improve. PCI Express evolves to give you better bandwidth, to give you less latency, etc., etc. But at the moment, this is still problematic. So that also means that if you have a compute node in which you have multiple GPUs, it really pays to invest in NVLink, which at least connects the GPUs to one another with very fast, very fast internal network, let's call it that. So your GPUs typically among one another will exchange data using NVLink rather than the PCI Express. Yeah, but your motherboards must support it and so on and so on. And you must be able to buy H100s. Good luck with that at the moment. If you have plenty of time, you get some. We have some, but not many. So that's, yeah, one of the things. There was an article in Nature like 2 or 3 weeks ago, don't quite remember, with researchers complaining that they couldn't get their hands on GPUs. Basically, if you know that our good friend Elon Musk buys 100,000 H100s for his data center, then you know why researchers can't get them. Okay, anyway. But yeah, we have a few. So basically, if you if you have the patience for the queue, then you can try them out. Okay. So basically, yeah, one of the things is, and this will come back time and time again, it's very important where to place your data and to ensure that you minimize traffic between host memory and GPU memory. Because even if you have a unified memory model, such as NVIDIA GPU support, even then it's still data needs to move. From a programmer's point of view, you can think, okay, I can access everything everywhere. Yeah, that's true, but it still needs to move from one place to another. So basically, that is not really a solution with respect to performance, only with programming convenience. But anyway, so we create an array. That array, as you can see, has 1 million elements. So that is, well, largish, not very large. And the D type is float 32. Okay, so I can time this. Let me run it again. And this is, of course, purely on CPU. Nothing has happened GPU-wise. As you can see, it takes a while, but that's, of course, because of Timeit. Timeit is not going to run this once. It's going to run it multiple times. So that's why it takes a while. Much longer than a single execution. Before hitting return, I should have looked at the actual time it took. So 3 seconds. That is, yeah, not particularly impressive, I would say. This takes a while. Okay, yeah, we have an exponent, an exponential function. We have, I think, a square root in there as well. Yeah, we've got a square root. So, yeah, these are operations which are not particularly fast. That takes something between 10 and 20 cycles to execute, while just a multiplication or an addition, on average, takes a single cycle. So, yeah, of course, the function was designed not to be the fastest around. Okay. Let me switch classes because yeah, so the question is, what's this notation which I use? Well, in Python, you can use the underscore as a separator. So it need not be the 1000 separator. I mean, it would be grammatically correct to write something like, to represent 1 million, I could write 100 underscore 00 underscore 00. That would be syntactically correct. But of course, the intention of the underscore is indeed to serve as a 1000 separator. So that's a nice feature of Python. C++ has something similar, but it's the quote, a single quote, and you can also use that as a 1000 separator. To be honest, I have no idea whether C++ would be unhappy if you would do 100, if you would not respect the 1000 separating thing. I've never checked, but it's a convenience, and of course it makes reading numbers a lot easier. So I typically tend to do that, for integers at least. Okay, so 3 seconds, not really very convincing. Now, of course, what we can do is use Numba in order to vectorize this. Okay. I already mentioned I don't particularly like the term because for me it means something more low level and something different. But at the end of the day, what is going to happen here is that we take our function, which is decorated, and Numba is going to generate what's technically called a ufunc, so a universal function. And that ufunc is a function that you can apply to a NumPy array as a whole. You know that type of functions, you're very familiar with it, because if you do something like np square root, you can apply that to any dimensional array. And what it will do is simply apply the square root function to each element, regardless of the shape of that particular array. So NumPy offers you an API to create your own ufuncs. You can do that. You'd have to write some C or C++ code. You have to do the bindings, and that's very tedious work. It can be done, it's unpleasant. So yeah. One of the things that Numba has as a feature is that it allows you to automatically generate these ufuncs. The only thing you need to do is to decorate your function. So we're going to vectorize Gaussian, okay, and we need to specify a bit of information about the arguments of the function. And in this case, that's quite simple. It will return a float 32, and all its arguments are float 32 as well. So it takes 3 arguments, indeed, x, mu, and sigma, and it will return floating point number. So this guy here, that's a return type. These guys between the round brackets are the types of the parameters of our function. Okay. And then, of course, we can again do the timing. And as you can see, this is quite a bit faster already. We get down to 9.14 milliseconds. So basically, that is a factor of more than 100. Well, I can do that either. This will work. If I want to be explicit, I can also put square brackets and a column there. Then it knows. But given that this is the first argument, this would actually work as well. So basically, what it is going to do, it has to broadcast anyway. So it's going to take also the mu and the sigma, and turn those into arrays as well, in a sense, because it needs to do the same computation for each. So essentially, also mu and sigma will be cast into arrays in this particular case. Okay. Yeah. Questions?
So the add vectorize, and then you have float 32 brackets, and then 3 times float 32.
Yeah.
So that means you're returning a float 32.
Yes.
And you, okay.
Yes. So the first float before the round brackets is return type.
Right.
So that's our float 32, and then the 3 float 32s in the brackets are in fact the representer types of the arguments. Yeah. Okay. So that was quite easy. Now, how do we get this to run on a GPU? Well, it's really, really simple. The only thing which we need to do is we need to add target CUDA. Okay. So let's see what we get. Okay, I'm going to do it the second time because I think that I'm a bit surprised. It should be lower, and it's not. Okay, it might be that in this particular case, because I'm running on my local GPU, and my fan has been spinning already since I started the Blackboard session. So I think my GPU is otherwise occupied. So take the numbers which we get today with a little grain of salt. That's of course.
In my case, it's 3 times faster.
Yeah, that's what I would expect. That's what I would expect. It's probably not going to happen for me because of the load, the other load which is currently on the GPU. We can have a look because of course this is a Windows machine, so I can use okay, come on, where is it? Here it is. I can check the performance here and see what my GPU is doing. So that would be GPU 1, because GPU 0 is the one which is on the Intel chip. So that's the discrete GPU, which is only doing graphics, so that's not particularly interesting. But this is actually the one which is computing. And as you can see, stuff is happening on it all the time. It's 25% busy, 26% busy, and so on and so on. So basically that will increase quite a number of things like latency on the one hand, communication with the GPU as such, and also of course some of my memory bandwidth is going to be eaten up by doing all kinds of stupid things on the screen. So that is a bit annoying. So yeah, take the numbers with a grain of salt. I'll first look at them before I hit return, because the numbers which are in the notebook are in fact done when the GPU was idling, when it was not doing anything fancy. Okay, so yeah, I would indeed expect something like 2.5 milliseconds or similar. So basically you would get a speed up. Now, of course, that strongly depends on a couple of things. So one thing is, this is not really a brilliant benchmark. Any idea why this is perhaps not such a good idea, or not really a fair comparison? Okay, I have to switch things here because otherwise I don't see the comments. Switch classes. In that case, yeah. So it will strongly depend. So yeah, what I didn't mention, and I should have mentioned because otherwise we're again comparing apples with oranges. So basically the CPU in this machine runs at typically 4 gigahertz, so it's really fast, and it also has 8 physical cores. So I get a very good CPU performance. If you do that on a commodity laptop, yeah, it will be significantly slower. Okay, then another question. No, not particularly. So basically, are the operations too complex, like exponents and square roots? Yeah, they're sort of complex. So that's not nice. But on the other hand, do we care? In the sense that, yeah, we have to do them anyway. So there is no escape there, typically. But yeah, of course, there is hardware support for this type of operations. Certainly in GPUs. In this GPU, that's a little doubtful. There will be some support for probably a square root, an exponential, well, maybe not. So basically, that does make a difference. We can run the notebook later, maybe, if I can get some compute time on a GPU and see the difference. That might be interesting. Yeah, of course, my question was basically, why is it not a good benchmark? So the complexity, no, that should be fine. That's okay-ish. But daemons, yeah, of course, this is a busy Windows system. Windows is not exactly known for being friendly to computations because lots of stuff is going on. I have probably something like 10 tabs open in Google Chrome, which basically means that I lose half of my memory and probably 90% of my CPU just on Google Chrome. So yeah, that's not pretty brilliant. And of course, the benchmark in this case is also skewed because the GPU is busy. So everyone's busy. So no, in that respect, it's certainly not interesting. But implicit D to H and H to D, okay, of the input arguments. So H to D, D to H, so host to device, device to host. Yes, so the reason why this is not necessarily a brilliant benchmark is indeed has to do with transfer of data. And the problem is that in this case, I don't have a clue when the data is transferred. So it might be that NUMA is sort of pretty smart with respect to memory management, and it notices that each time it's called with data that it already moved to the GPU and is computing on that data without having to transfer it. So now the question is, what are you doing? In the sense that, what are you interested in? Are you interested in the time it takes to execute this once? Okay, in that case, the time is likely to be dominated by the time it takes to transfer data. Okay. Then, on the other hand, if you do this multiple times, can you do it? Can you do your computations on data that is guaranteed to reside on the GPU already? In that case, you pay the price for transfer once, and then you have pure compute. So in this case, I have no clue what is happening. I can't see what is happening, so I don't know whether each call to is going to actually transfer the data or not. So in that respect, it's not really a controlled benchmark. Now you can argue similarly, of course, for the CPU part of the benchmark, because I'm operating on the same array over and over again. That array has a length of 1 million elements. So that's 1 million 32-bit floating point values. So that's 4 gigabytes. Okay. On this particular laptop, that array is going to fit entirely in last level cache. Because I think this machine, if memory serves, is as something like 5 or 6 megabytes of last level cache. So that's entirely going to fit in there. So the first time I run Gaussian, what was it? Gaussian Pure, or the vectorized version for that matter, it doesn't matter. I'm going to pay the price of transferring my data from RAM to last level cache, to L2, to L1, etc., etc. But the second time around, I don't have the memory transfer from RAM to cache anymore. It will just be likely in last level cache. On this laptop, which again is pretty busy, probably not, because in the background, Chrome has decided that it should definitely update the LinkedIn stream, whatever. And basically it eats into my cache for you. But on a CPU node, on a compute node, you would definitely notice that. So yeah, what are you measuring? That's always the question which you have to ask yourself if you're benchmarking things. So in that respect, this benchmark is a bit iffy. Let's put it that way. It's definitely not well done. Okay. So what we can do is to ensure that we measure what we want to measure. Okay. What do we want to measure? Yeah, I don't know. What do we want to do? So you might want to know how much time it takes to get your array from host memory to GPU and do your computation and have the result. That's it. If you want to do that, don't use time it. Use time. And then modify your array. Do it again a couple of times so that you actually do have an average. But then you have to make sure that in each iteration which you do in order to benchmark, that you actually do the memory transfer. Okay. On the other hand, if you're interested to know, well, okay, my data is on my GPU anyway, I put it there in advance, and then I want to know how much faster my function is, then you should put your data there first. And this you can actually do. And one way to do that is to say, well, okay, I'm going to do an explicit transfer. And that's here in cell number 9. So basically, we get an object xdef, which is an array, but it lives on the GPU. So we are going to transfer to device. That's why there is CUDA to device. And what we're going to transfer is the content of X. Okay. So basically, we can get that array. So the values you can get. So basically, I do the values here because I also want to make sure that the result is going to be stored on the GPU, so that I don't get an implicit transfer of my results back into the CPU without it being under my control. So I've got two arrays. Okay, the first array is initialized in the sense that it has the values of X. The second array is not initialized in the sense that memory is allocated on the device with the same shape and the same D-type as X, but it's not initialized. Why would I? Because I'm going to put values in those memory locations anyway. So why would I waste time putting something there? It will be done anyway during my benchmark. So compare that to npempty in NumPy. You allocate memory of a given shape of a given D-type, and you will fill in the values of that array later on. That's the analogy here. Yeah, exactly. So indeed, everything now is going to happen on the GPU onwards. You can also only compute on these device arrays on the GPU because they only live on the GPU. And there is no automatic updating between X and XDEF. So that's something that you need to take into account. If you want the values either of XDEF or of our array values, our device array values, we'll have to explicitly fetch them. So there is no direct coupling between, on the one hand, our host array X and our device array XDEF. So that's something to keep in mind. They're not synchronized magically somehow. Okay. So now we can time the same thing, but rather than use the host array to call our function, and note this is still the GPU function, I'm actually going to use the device array, and also I'm going to place the result of the computation into the array values, which is also a device array. And this you can do because that's what Vectorize supports. It augments your function. It adds an optional argument out, which allows you to specify where the results should be. And that's specifically for running on GPUs, because now everything is happening on the GPU and on the GPU only. So this computation indeed is pure GPU. And as you can see, it was of the order of 700 something microseconds. So that would be, you would have to compare that with 2.5 milliseconds originally. So let's see how it pans out now. Now we have 2 milliseconds. Again, this thing is crazy busy. So it would be a factor of 5, and that is more or less consistent. Because 2.5 divided by 800 is something like 3-ish. If I divide 9 by 3, I also get something 2-ish. So basically, the factor which we gain is similar. Only probably your numbers will be better if your GPU is not involved in other things. But as you can see, this is a cleaner benchmark if you want to know how fast your actual computation on the GPU is, without having to bother with transfers between device and host. And that was, of course, included in the first benchmark. So which benchmark is correct? Can't tell you. Depends on what you want. But you need to be aware that they are different and that they answer different questions. Okay. Now, of course, one of the things I've been cheating a little bit, and out of curiosity, I would want to know. So the first implementation, Gaussian Pure, was of course pure Python, in the sense that if we just go back to it, this is really not something you should do at home because it's really, really bad code. But it was to ensure that I could more or less fairly compare with pure Python and then doing something a bit smarter. So basically, what you see is, in the first place, I'm doing here a type check. By the way, this is bad style in itself because I should use instance of, but okay. Let's skate over that. I'll change that later. But basically, if this is an iterable thing, then I'm actually going to use map and list and so on. So basically, I'm doing an explicit iteration over my whatever I put in. Okay. This is really not pretty brilliant. So of course you wouldn't write that kind of code. What you would do is, of course, assume the input of my function is going to be a NumPy array. So I'm going to use ufuncs npx np square root in order to do that computation. So that's actually what's happening here. Okay, and just for the sake of comparison, we're also going to compute this, or to time this. And then you see that we get 6.6 milliseconds. So if you compare that to the GPU with transfer, it's actually faster. So for this particular computation, in fact, using the GPU would not help you, in the sense that it would actually be a little slower. So yeah, that's the kind of consideration you have to make. So when would I gain? When my data is on the GPU and I keep my data on the GPU while I'm computing. Then I'm gaining. And then I'm gaining significantly with respect to the CPU. Basically, I would gain a factor of 3, approximately. And that is, for this hardware, a fairly realistic number. Okay. Just for the sake of the argument, I would like to know whether my results are similar. And of course, they won't be equal as such. So I'm going to use the np all close function in order to compare the values. So basically, this allows me to do a comparison at a potentially given level of precision. In this case, I just assume the defaults, but I could set here a relative or an absolute tolerance in order to do the comparison. Okay, so that seems all right. Then, of course, we can make a plot of the values, which is not particularly exciting. Okay, so this was a simple example of how to use a GPU using Numba. Essentially, quite simple. We use the vectorized decorator, and as a target we set CUDA. That's it. And of course, what we can do, if it's applicable, is to use the CUDA to device function or the create on device in order to ensure that our data is locate it where we want to locate it. Okay, let's consider a different example. So what we're going to do is we're going to compute pi in a really inefficient way. There are many ways to compute pi. This is not exactly the most efficient one, but it's one which is fun because it allows to illustrate two things. One of them is how to use random numbers on a GPU, how to get random numbers on a GPU, and the other is because it parallelizes really, really well. This is essentially parallel. This is essentially embarrassingly parallel, so that always helps. So in that respect, it's an interesting example, and in a way, it's a model for all kinds of Monte Carlo methods where you basically work with distributions and you simulate things. Okay. So this would be the implementation. So it takes just one argument. The function takes one argument, and that is the number of tries. So what am I going to do? You could compare it to throwing darts at the board. The board is square, but it has an inscribed circle. So basically, if we say that the radius of the circle is 1, then the sides of the board would be 2 by 2. That's basically the idea. Okay. And now I'm going to throw randomly. In my case, that would indeed be the case because I'm very bad at this. So I just throw randomly darts at the board, and I'm going to count how many land in the circle and compare that to the number which I threw. That gives me pi if I divide, no, if I multiply by 4 and divide by something I forgot, yeah, the number of tries. Then basically I get a value of pi. Not a good way to do it, but anyway, it works. So in code, simple, we have the number of hits, which we initialize to 0. Okay. Then for the number of darts we want to throw, I'm going to determine the x-coordinate, the y-coordinate, and I'm going to compare whether that falls into the circle or not. Of course, what I could do is compute the distance to the origin from of that point, and the distance would be the square root of x squared plus y squared. I'd have to compare that to 1. Yeah, the square root of 1 is 1, so I can just leave out the square root for the distance. And as I already told you, that's not a bad idea, since the square root is an expensive operation. If I can avoid it, it's a good idea to avoid it. And in this case, I can happily avoid it, because, of course, if I compare a distance, I can just as well compare the square of the distance. So it's always the same thing. So why would I compute the square root? Okay. And then, if it happens to land in the circle, then I increment the hits by 1. And finally, pi is 4 times the hits divided by the number of tries. Okay. So quite convenient. Also note, by the way, I decorated this with NJIT. So basically, I'm asking Numba to generate C++ code for it, compile it, generate bindings, etc., etc. Okay. So as you can see, it is not so very reasonable. We get 3.14, but then we should get 592, which we don't. So yeah, that's what I meant by it's not a brilliant method to do this, because actually we have 100,000 iterations here. That means 200,000 random number generations, generating 200,000 random numbers. That is expensive. Random number generators are not your friends with respect to performance. So basically, doing 200 of these and then getting a crappy result, yeah, well, but okay, it kind of works. All right. We can assess the precision of this. So basically, we can make sure that we well, we can look at how many iterations, how many tries we should have in order to get a certain precision for pi. So that's basically this function here. So the number of tries is going to be orders of magnitude. And in NumPy, you have this nice function which is called log space. And so basically that allows you to generate functions that are by factors apart rather than linearly spaced, such as linspace. And in this case, I would be going from 2, so that's basically 100, up to 9, so basically a billion. Do I have my, yeah, I think I have them correct. Yeah, I think that would be sort of correct. Okay. And then after a while, you get this plot, and that gives you some idea and shows you that this is not really the most brilliant way to do this. I should have added timing information. That would have been smart, but okay. Okay, so here it is. So remember, this is a log-log plot. So it goes in orders of magnitude rather than linearly. And as you can see, for 200, we get a precision of 10 to the minus 1. So that means you get 3 dot some number. At least the 3 is right. And you really have to go up quite high to 1 billion iterations in order to get to a level of 10 to the minus 5, so to, let's say, 5 significant digits. So yeah, don't do this at home. If you want pi, there are better methods to do that. But anyway, it's always interesting to do this kind of comparison. Okay, now what we want to do is to do this also on a GPU, and we want to compare. So the number of tries on the GPU will be expressed in terms of the architecture of the GPU. So I didn't mention that yet because we didn't go into the details about GPUs. But GPUs actually consist of multiple, let's call it modules for now. Typically in NVIDIA speak, that's an SM, as an streaming. What's the M for? I think multiprocessor or something like that. I forgot what the M stands for. Everyone calls that an SM, so basically. But basically what it does, it is a compute unit, let's say, on which multiple threads can run in parallel. Multiple threads being at most 1024. That's the limit of your SM. And basically you have multiple of those. Depending on the make of the GPU, it can have, I don't know, 5 up to quite a lot. Don't know by heart. Doesn't really matter. You have to check for the hardware you want to run on. And I tend to forget how many they have. I'll show you later how to see how many modules, how many SMs it actually has. Anyway, so what you will typically do, since you have more iterations than 1024 typically, what you typically will do is to decompose your iterations into blocks. And you can have essentially as many blocks as you want, and such a block will be executed on an SM. That's going to run that way. So the blocks essentially give you a way to also deal with load imbalance, which in this case we wouldn't have. But basically, you can view a block a little bit on a, let's say, on a conceptual level, as similar to what you would do with OpenMP, with your scheduler. It would also decompose your iteration space into parts and execute those separately. So that's the same with your blocks. So I want a total of, in this case, 4,069 blocks, and per block I want 128 threads. So I can go up higher, but depending on the type of computation you do, it's better to, it may be better to limit the number of blocks to something a bit smaller. And then I set the number of tries as 1024 times the number of blocks times the number of threads per block. So essentially, I would get something that's 2 to the power 10, 2 to the power 14. So that is 2 to the power 24 plus 2 to the power 7. So something like, no, that seems a bit too much. No, it's not too much. Power 7, yes. 24 plus 7, 2 to the power 31-ish, something like that. Yeah, 31. Okay. So if we want to do that on the GPU, we can, on the CPU, we can do that. And as you can see, it took 3 seconds, so likely it's going to take a little longer now, since my CPU is busy. Okay, 4 seconds? No, not too bad. 30% more than on an empty system, so reasonable. Okay, so question, how are we going to do that on GPU? Okay, we might hope that we can vectorize blah blah and so on, just like before, but yeah, that's not going to cut it, because our code is not going to run on GPU. Why? Well, the culprit essentially is these guys here, random. That's just not going to run on GPU. So maybe a bit about random numbers. You're likely quite familiar with them, but just to make sure that we're on the same page. So we don't generate random numbers. Well, we can generate random numbers, but typically we don't. What we do is we generate pseudo-random numbers. Why? Because we are scientists, we want to be able to reproduce things. So how do we do that? We fix a seed. We seed our, that's just an integer or an array of integers, depending on the particulars of your random number generator. But typically it's just an integer. And we seed our random number generator with that. And if we do that, we always get the same sequence of random numbers. Okay? So what that means essentially is that somewhere under the hood, the random number generator keeps track of this, the state it is in, because it will generate the next random number, based on the previous random number, not necessarily exactly based on that number, but based on the state it had. The state changes, and it will generate new random numbers. So there are many random number generator algorithms, or I should really say pseudo-random number algorithms, and depending on their complexity, it takes longer to generate random numbers, but you get random numbers with interesting statistical properties, because what you typically don't want is that random numbers start to autocorrelate, and you also want that they are close to a certain distribution, like for instance a uniform distribution or whatever. So basically the quality of that depends on the algorithm. The more complex the algorithm, typically the better the statistical quality of the resulting random number distribution, but that comes at a price. It's kind of expensive. Okay. Why am I saying that? Well, basically what we need is some mechanism to keep track of the state of our pseudo-random number generator from iteration to iteration. Okay. But we want something else. And that problem is not restricted at all to GPU programming. Because what happens when you have multiple threads in your program? You don't want each thread to generate the exact same sequence of numbers, because typically they are supposed to do different things. So each thread would need their own individual sequence of numbers. Okay, how can you solve this? You are easy. The thing you need to do, well, you need to do several things, because this is a big pitfall in parallel programming if you just start out with it. But what you need to do is to make sure, on the one hand, that you have a unique seed for each thread, for each random number generator. And the second thing is you need a random number generator that is thread safe. If each thread under the hood uses the same random number generator, you will be in trouble. Why? Because typically this random number generator will be used in a tight loop. So there will be many accesses to the state. One access for each thread that's asking for a random number. So you get a lot of contention for the same memory location. And you will have a major slowdown of your code, because that part is actually going to happen serially rather than in parallel. So, okay, not a problem if you are aware of it. There are random number generators that actually are thread safe, that you can call from multiple threads, no problem. Typically, in general, let's put it that way, in the standard C library, you have a family of functions that start with R for reentrant. So basically you have an R underscore round. So basically a reentrant, a thread safe version of the random number function. Okay. So that's cool. But of course that comes at a price, in the sense that if I have 16 threads, it means that I need to keep track of 16 state vectors for each of the threads. Each thread needs its own state vector to generate an independent sequence of pseudo-random numbers. Okay, so that's nothing new, we know. Parallel Programming 101, OpenMP, we know that that's an issue. Okay, but of course this is the same thing. If we now start running computations on a GPU, we have the same problem, but multiplied by a pretty huge factor. Because now many threads will be running on a GPU. 10,000s, maybe 100,000s of threads are on a GPU, and each of them needs to have state. And that is a bit unpleasant. And of course, the random number generators, which are typically used on CPU, are not really suited to be directly implemented on GPUs because of that issue. Because the state space would get really, really large, because it is just linearly proportional to the number of threads which are in your application. which is huge on GPU. So that's why we need to rewrite our code in order to use a random number generator that works properly on a GPU. And that's why we did the import back at the beginning here. We did an import here, create Xoroshiro 128p states, and basically this Xoroshiro is essentially an implementation of a random pseudo-random number generator on GPUs. Okay, so that's what we will have to use. Otherwise, this is not going to fly. So this is the implementation, and as you can see, it's actually not that different. We also have as an argument the number of tries, and in addition, we are going to write the result into a variable. So basically, that is also the third argument. But the first argument is the random number generator states. So I'm going to explicitly pass into my function the random number generator states. Okay. And now, of course, I need a bit of additional bookkeeping, because you can view this random number generator states as an array with equal size as the number of threads. That's easy. Okay, but since now each thread is going to do its own computation and needs its own state, we need to know which thread that is on the GPU. And this is easy to get because basically there is a function in that CUDA module which is called grid, and this is a one-dimensional grid. Grids can be one-dimensional, two-dimensional, three-dimensional. There it ends. But basically, this is one-dimensional grid, hence grid 1. And that will give me the index of the thread that is executing this code. You can compare that if you want, similar in spirit, to get OMP thread num. So basically, it gives you the thread ID which is being executed. Similar, MPI get rank, same thing. Okay, so once we have our ID, our thread ID, it looks very similar. But now, of course, we don't call Python's random function, but we call the Xoroshiro function, and what we want is a uniform float distribution, float 32. Okay, we specify the states and we give the index. So that means that the algorithm, the Xoroshiro algorithm, can generate the next random number based on the state we are giving. It will update the state, and it will do that for the right thread because we also specify the thread index. And that's basically the idea. And apart from that, the only thing we do is the remaining thing which we do is we store the result of each thread into the results array. Okay. Notice that now we no longer decorate with vectorize, but rather with CUDA JIT, so just in time. So this is a different generator because it needs to do a bit more work, and you need also access to that index. Okay, come on. Why aren't you executing? Okay. All right. So basically, this is the kernel, and this is something that, in a way, you can very well compare to actual CUDA code, because the CUDA code for this in C++ would not look that different. The details would vary a little bit, but you would indeed also get the index, and you would also have to pass an array containing states, and you would also have to call some function to generate random numbers specific to a GPU. Okay. Now, of course, this is a nice function, but we can't call that directly. We'd have to back it in a little bit in order to get that properly running without us having too much to do. Okay, so basically we write sort of wrapper function, and that takes 3 arguments: the number of tries, the number of blocks, and the number of threads per block. Okay. So the first thing we need to do is to create the states, and that's with the create Xoro 0, etc. states. So we specify the number of threads in total, and that's going to be the number of blocks times the number of threads per block. Okay, and then we also specify a seed, and okay, I'm just initializing it here with a random number, a random integer between 0 and 100,000, whatever. If I want this to be reproducible, I would of course not pick a random number as a seed, but a given integer, some given integer. Okay, so that's nice, we already have that. And create Xoro 0 function is kind enough to give us a device array. So this RNG states is already on the device. We don't have to put it there. All right. Next thing we already know, we want the results, and we want them to be in the device. So we immediately, in one go, create a host array with NumPy functions and allocate it on the device, transfer the data into the device using CUDA device array. Okay. Sorry, we create it immediately there. We don't create a NumPy array locally. We directly create an array on the device. So that's different. We don't even have a host array here. Okay. And then what we need to do now is we have our function compute by kernel. Remember, that was this guy. And it was annotated with CUDA-JIT. Okay. So in case you're not really familiar with what decorators do, what they actually do is take the function they're decorating and write a wrapper around it. So the result of applying a decorator to a function is a different function that may have different arguments, that may have other wrapping around it. And here, what it actually returns is not really a function. Because if you would check what the type is of this compute by kernel, then actually it's not really a function. It's actually an object, and an object where the square brackets, but I always forget which underlying dunder function that is, but that has been overloaded. And so basically you see these square brackets here, and they seem to be applied to the function. So that might seem very weird. We're kind of treating our function as if it were an array or a dictionary or something that we can index. Okay, so what the heck? What is essentially going on under the hood is that the corresponding dunder function, which I should really look up, has been used. It implements basically the configuration of your function object, so that it has additional information for how to execute this kernel on the GPU. So between the square brackets, we tell it how to execute. And what do we say? Well, we give it the number of blocks and the number of threads per block. And that is indeed information that the GPU needs in order to schedule our computation on its hardware. So that's essentially what's happening here. And then the actual call, that's just the arguments as usual. So basically RNG states, then the number of tries and the result. Okay. So for those of you who are familiar with CUDA, this is what you would put between bracket, so less than, larger than. That would also be the number of blocks and the number of threads. So we kind of do the same thing here, only we don't need new syntax for it, which you do need in C++, well, in CUDA, because C++ couldn't help you much there, because it already, with templating, yeah, you could try, but it's not the choice that the CUDA developers have made back in the days. One of the reasons is also that, of course, CUDA predates C++ 11 by quite a bit, and many of the things that would make this more palatable in C++ has been introduced in C++ 11 and later. So yeah, they needed their own notation. But in Python we don't have to, because we can actually override the relevant dunder method and use that in order to configure our kernel to run on the GPU, to give it the parameters it needs to execute on the GPU. Okay, so then what we want to do is to make sure that once we launch our kernel, so once we do our ComputePy kernel, that actually finishes. Because the last thing we need to do is we need to get the computed results onto the CPU. And that's the last line here. That's computing the sum of that result. So this is our actual computation of pi. But suppose that we didn't have the CUDA synchronize, then we would actually, with high probability, reach the return statement before the CUDA computation was actually finished. And we would have a race condition, because we would get indeed the result which is at that point in time on the GPU, but it might be that quite a number of elements in that device array have not been updated yet, have not been computed yet. So that's why the CUDA synchronize is there, and why the CUDA synchronize is really crucial, because that ensures that after the CUDA synchronize, that the kernel has finished computing. And then, of course, it's safe to get data off the device and into the GPU. So this is a little more complicated and quite a lot closer to CUDA itself. Okay, let's execute this. And let's compute, because in the first place we want to know whether that works or not. And as you can see, we do get 3.1417, etc., etc. It's about as good and as bad as the CPU version, obviously. In this case, they won't be identical because I use random seeding. So I can't expect the same results, the exact same results. Also, even if I were to specify the seed explicitly, both for CPU and for GPU, I would still not get the same results, because the algorithm which is used in order to on the GPU versus on the CPU is different. So even with the same seed, I would get a different sequence of random numbers. So I would certainly get a different result. There is nothing I can do about that. So here I can never do a one-to-one comparison because algorithms are different. And anyway, again, that's not even something that has to do with the algorithm as such. The cause is even deeper, because even if you do that on CPU, use the same algorithm on a non-parallel and a parallel computation of pi, you would still get a different result. Why? Because if I do this in a serial way, I would have one sequence of pseudorandom numbers, perfectly reproducible each time, no problem. Okay, if I do that in parallel, okay, the first thing I need to do is to create random seeds for each thread. So even if I compute the same number of random numbers, pseudo-random numbers, they'll still be different between the serial version and the parallel version. So that's already, again, something related to random number generation, why even on a CPU, I couldn't do a one-to-one comparison. But it's worse, because basically on if I would do that, and even if I would have at the end of the day all the same random numbers, even then, if I do that in parallel, the probability that I would get the exact same number is again not so high, because I would have to add all these numbers, and depending on the order in which I do that, I'll get a slightly different result. So basically, reproducing this up to any number of significant digits is just not possible. So that's something that you need to keep in mind. I'm stressing it here because basically you might think, well, okay, if I take the same random seed for the CPU version and the GPU version, I'll get the same thing. Yeah, no, you don't. So that's something to be aware of. Also, when you write tests, if you compare your CPU implementation with your GPU implementation for correctness, something that you need to take into account, that if it involves random numbers, it's not going to be the same. Also, if it involves aggregating numbers, it's not going to be the same, because you have many threads on your GPU. The addition will be done in some order, and that will influence the outcome. And addition for floating point numbers is not associative. It's not communicative. It doesn't commute. So basically, this is something that you need to be aware of in the context of parallel programming in general and GPU computing specifically. Okay, let's time this. 142 milliseconds as compared to, if memory serves, 4 seconds. So basically we get a very nice speed up here. Okay, is this a fair comparison? Yes and no, depending on your point of view. Well, in a way, we are again kind of comparing apples and oranges a little bit, because the pseudo-random number generation algorithm on the GPU is significantly simpler than that on the CPU. So basically, that has an impact. The quality of the sequence of random numbers which we get on a GPU will not be as good as that on a CPU. So basically, we're cheating in the sense that the workload for the GPU is less than that for the CPU, since we used a very decent random number algorithm on CPU and one of lesser quality on the GPU. Less work, So yeah, it also explains part of the performance difference here. Okay. Question. Yeah, sure. It's of course the outcome of the thing that counts. It depends on, of course, it depends on what you're doing. If you have your Monte Carlo simulation and you're simulating, for instance, let's say radiation, simulation of radiation in materials, it's likely not going to matter. On the other hand, if you are doing MCMC methods and you are inferring marginal distributions, you might not be very happy with the GPU quality of your random numbers, because there might be too much correlation. There might be not good enough with respect to the desired distribution and so on. So it depends. For some computations it will be fine. For some computations it might not that fine. But it depends on what you need to achieve, as usual. So in this particular case, it's perfectly fine because I know that my precision is crap anyway. I mean, the resulting precision of pi is crap anyway, however I do it. If I need 1 billion iterations to get to a precision of 5 significant digits, yeah, that's something where the quality of the distribution really is not going to do much for us. Okay, so again, we can plot the resulting precision. And as you can see, it's quite similar. We start off at 10 minus 3, in this case for 1 billion. So the x-axis here is different. For CPU, we started at 10 to the power 2, so 100 tries. Here we start at 1 billion. So that's why we are already at 10 to the minus 3 at the left side of the plot. I just did it this way for 2 reasons. Basically, I'm bound here by the number of blocks and the number of threads per block. And hence that explains the large number to start with, basically. Okay, apart from that, it doesn't matter. We get, for 1 billion, we get down to approximately 10 to the minus 5. And this is very similar. Okay, we can compare a little bit. Let's see. Yeah, it would be very similar, essentially. So that is reassuring. All right, let's do yet another example. Another nice example, which again you will recognize from Python for HPC, is computing the Julia set. So that's essentially, again, sort of embarrassingly parallel. And in this case, we start with a complex number, which we iterate. In each iteration, we square it, and we add a constant complex number. Right, so there was a second part of the question which I didn't read. Before I start the Mandelbrot thing, let me maybe read that. Yeah, okay, yeah. So, yeah, that was discussed. All right, we start with a given complex number. We square it, we add a constant to it, and we do that iteratively up to 2 conditions. One is the maximum number of iterations. That's something we fix in advance. And the other thing is that the norm of that complex number should be less than 2. That's the idea. Okay, now we don't do this for an individual complex number, we do this for the complex plane. And then we are interested in the number of iterations. because for some complex numbers, this is going to diverge. So the norm is going to be pretty quickly larger than 2, hence we stop. For some numbers, this does converge, and at least in the number of iterations, and basically the value of the norm of the complex number will not exceed 2. So that's basically what we do. It would be nice if I had a plot. Maybe I have one somewhere. Okay, so this again is a good job for vectorize, if you want to do that on the CPU, because basically what we want is a ufunc, a function that we can apply to a NumPy array with complex numbers. Okay, so this is our function. Let's first go through that. So we have a complex number z. That's the one which is going to be updated all the time. We have a complex number c. That is fixed constant. And then we have the maximum number of steps. So those are given. And then, as you can see, we're going to compute the norm of the complex number. And you can already guess why I'm doing it this way and not with, for instance, NP apps or CMount apps. Basically, that would compute the square root. I don't want the square root. This is the same argument as I used with the distance to check whether it was in the circle or not. This is the same thing. The complex norm is not different in that respect from a distance. Since I want to compare that to 2, if I just square the real part and the imaginary part added, and compare that to the norm 2 squared, I have the same thing. So again, I'm saving a square root here. Okay, but then actually this should be 4, not 2. Okay, doesn't matter. We want to keep the GPU busy, so that's fine. The result is not going to be correct with this implementation because this should be 4, but yeah, whatever. And we also check the number of steps. Okay, so in each iteration, I already said we update set, and we increase the number of steps by 1, and then the final result is the number of steps, and that's the idea. So that's an integer. Okay, now what you typically do, because you want to make nice appealing plots, is limit the max steps to values between 0 and 255. So basically you want all your steps to be between those numbers. Why? Because then you can make a nice grayscale plot where 0 up to 255 is basically the intensity of your plot. Easy in a grayscale plot. All right. So if we indeed limit max steps to 255 at most, then of course our function can return a uint 8. Because basically that's an unsigned integer with 8 bits, which means it can represent values between 0 and 255. Okay, hence the return type of this function is indeed uint 8. It has a complex 64 as arguments. That's for Z and for C respectively. 64 bits means it is single precision. 32 bits are used for the real part. 32 bits are used for the complex part, the imaginary part. In total, 64 bits. Okay, and then we have an int32 for the max steps. Yeah, okay, I could have chosen uint 8 as well, but whatever. And the target is CUDA, so I'm going to immediately run this on the GPU. Okay. So of course now we need our input. So yeah, we need complex numbers in a plane. And basically the easiest way to do that is to generate all the real parts and all the imaginary parts. So that's with NP linspace. And as you can see, we go for the real part and the imaginary part for numbers between 1.8, minus 1.8 and 1.8. So we have a square in our complex plane. And basically d-type again is float. All right, that gives us the real part and the imaginary part. Now, of course, we don't need that. We want complex numbers, a matrix of complex numbers. So this we can obtain in 2 steps. The first step which you take is we do a mesh grid. That's going to give us 2 square arrays. So 2-dimensional arrays, 2 matrices if you want, square matrices, with all the x values and all the y values. And from that we can compute another square array with complex numbers, just by adding the 2 after multiplying y by the complex constant I. In this case, in Python is j, but okay, that's for engineers in the States. Okay, so that gives me a 2-dimensional array of complex numbers. All right, and that should of course be a 1000 by 1000 array. We can verify that if you want. So the d-type is COMP64, so that's good. And let's verify the shape. So that should be 1000 by 1000. Okay. Then additionally, we need a complex number, a complex constant, and let's see. You can take different values that will give you different shapes. It's nice to play with, but basically this is the one I take here, and the maximum step is going to be 256. And now I need to check whether there is a less than. Unfortunately, yes, there is. Okay. So basically, that's it. That's my arguments. And then I can compute the image. And the image is going to be my Mandelbrot function applied to this square matrix with the given constant c and the max number of steps. Okay, that was fast. So let's have a look what type image is. And as you can see, there has been an automatic conversion because this happened on the device. So now I have a NumPy array that's on the host, and basically the d-type is uint8 as we intended, and the shape, let's check it, but you can imagine that it is 1000 by 1000. Okay, and then we can visualize it basically. And as you can see, it looks nice. Whatever. At the end of the day, it's just an image show. I just fiddle a little bit with the axis in order not to get labels because I don't care about the labels here. All right, so basically that is not so much harder than doing this on CPU. The only thing which we need to do is to specify vectorize and then give the signature of the function. That's it. Okay. So what happens if we do that on CPU? So basically this is again the same thing, but now we don't specify target CUDA. We let this run on the CPU. Okay. This we already had. Don't know why I have it twice. Okay, so again we generate our data. Now notice this is larger. Now we have a 10,000 times 10,000 matrix rather than 1000 by 1000. So this is going to be 100 times as big. So question number 1, always of course, does it fit? 10,000 times 10,000 is 100 million. It's complex numbers, so that means 8 bytes. So that is 800,000 bytes for Z. And we also have to count the integer array, 10,000 by 10,000, again 100,000. But yeah, that's a uint 8, so that's only 1 byte per element. So we are at, if memory serves, 900 megabytes. Okay, that fits easily into the memory of a GPU. But that's something to take into account, because if I go larger and I exceed the memory of my GPU, I will of course get an error. Then we'll say out of GPU error, out of GPU memory or something like that, and it's going to fail. So there's always a consideration which you have to take. Okay, how large are my data types? What am I going to store on my GPU? Can I actually store it in the RAM of the GPU? In this case, no problem. Okay. Again, complex constant, the number of iterations. Okay, let's do that on CPU. So that's probably going to come out now at approximately 1 second. Yeah, okay, 800 milliseconds. That's not too bad. Let's do it on GPU. And as you can see, this is a bit worrying, because for this particular benchmark, in the circumstances on my device, on my computer now, actually the GPU version is a lot slower. It wasn't that bad without a loaded laptop, but still, as you can see at the moment, we absolutely don't gain from the GPU. On the contrary, running this on GPU is in fact slower. But of course, we know why that's the case. It's because the data is transferred continuously back and forth between CPU and GPU memory. The Z matrix is 800 megabytes. The result matrix, or iterations matrix, or whatever I call it, is 100 megabytes. So that goes back and forth all the time. And of course, if you just have a million numbers, okay, you pay the price of the latency. But if you also have a large matrix, you also are going to pay the price of, on top of the latency, the bandwidth. And as I already mentioned, bandwidth between CPU and GPU memory is not the fastest thing around. So that's what you see here in this particular benchmark. So the larger your data is, the more careful you need to be, so that it's in the place where you actually need it, at the time when you need it. If it gets shuffled back and forth, you're going to be unhappy. Okay, so let's do this again, but now create device memory. Again, simply both for our complex matrix and for our result. And if we time then, yeah, you see that it's better, but still, again, in these circumstances, actually, in these very particular circumstances, the CPU is still faster. Okay, again, that's not 100% fair, because I still exploit caches on CPU. But given the size of the data, that effect will be very small, because my last level cache is at most, I can check later, but I think it's 5 megabyte resource. So my array is way larger. So this will not exploit caches much. But yeah, okay, I've got my 16 threads, which are doing the work. So basically, that will actually give me a performance edge here. Okay, so essentially, if you visualize, now this really takes some time, because getting a 10,000 times 10,000 plot is really going to take some time. But as you can see, it's the same plot, but with a bit more detail. Okay. Now, there is a very good reason why this is not brilliantly effective on a GPU at this point in time. And that's what we will cover next. Oh, there. Why don't you stop me? It's 11 o'clock. You should really stop me when I forget to give a break. Let's have a break urgently. Are there any questions at this point? Okay. If not, let's have a break of, let's say, let's break till 10:15. That's a round number, and that gives everyone time for a toilet stop and getting some coffee, things like that.
Are we going to cover all 4 notebooks?
That seems to get more and more unlikely. The general problem is, with my trainings is that I always have way more material than I can actually cover. So, but the good thing is basically the things we're now discussing transfer to the other notebooks. So once you understand the principles of GPU computing and the reasons why things may not be as performant as you would hope, doing that with a different library is just more of the same. So whether I explain this with Numba or I explain it with PyCUDA or whatever, at the end of the day, it's going to be the same thing anyway. So the important part is the underlying principles. Yeah.
And the main bottleneck is always if you have to move data
Yes,
back and forth.
that's your main bottleneck.
Then it just
Exactly.
makes no sense.
No. And that's one of the things, of course, it's one of the things that you have partially under control, in the sense that suppose you really have a large data set, whatever data is here. I mean, it can be, for instance, parameters of a model you're training in the context of machine learning, deep learning, whatever, doesn't matter. At the end of the day, it's numbers which you need to move around. So if that data is much larger than you can possibly store in the memory of the GPU, what you will typically try to do is to overlap computation and data movement. So essentially what you would do is say you have arbitrary number, 16 gigabytes of RAM on your GPU. Let's take that as a ballpark number. Okay, now I can sacrifice memory and I can say, well, okay, I'm just going to use 8 gigabytes of memory for my actual computation. 8 gigabytes is free. But since my CPU is just sitting and twiddling its thumbs while the GPU is computing, I can use that time to fill the 8 gigabytes while the GPU is computing. This I can do. And then basically, once the GPU is done with its batch of 8 gigabytes, it starts on the next batch of 8 gigabytes. Meanwhile, I can extract data from the, transfer data from the device to the host, the results of my computation, and start to fill the 8 gigabytes which then are unused with new data. And that gives me overlap between data transfer on the one hand and computations on the other hand. That's also why typically if you launch a kernel on a CUDA device, that happens asynchronously. So if you call the kernel or if you launch the kernel, it will return immediately, regardless of whether the computation is done or not. And that's exactly to give the CPU time, the opportunity to do something meaningful. And that's also why you need to CUDA synchronize in order to make sure that once you get that data, that you are sure that the computation has actually happened. So that's basically the way to ensure these kind of things. And then, of course, you can get reasonable performance if your computation on the GPU is long enough to offset the time for the data transfer. And of course, once you're doing interesting stuff on your GPU, that is typically going to be the case. That the workload is enough on these 8 GB to give you time to extract data, well, get data from device to host, or move or move data from host to device. That's the idea. Okay. Going to make a screenshot of the participants for the certificates. By the way, for the people in the room, don't know whether anyone, yeah, if you know where to go, no problem, because that's what I'm going to explain. Toilets are at the other end of the corridor, so that's easy. If you want a soft drink or something, there is a vending machine. If you go left when you leave, right immediately into the next corridor, there are vending machines. If you want coffee, don't use the vending machines. You can use the coffee machines, which you see if you again turn to the left. You keep on walking. You walk straight onto 2 coffee machines. Please use the cardboard cups, not these ones which are provided, but which you won't see unless you know where to find them. If you know where to find them, don't use them. Use the paper cups. Okay.
Yeah.
Yeah, going to.
Unless you're logged in, because then I have it. If not,
Okay, yeah, I logged in earlier, but I logged in out afterwards.
I'll give you that.
I have a pen here somewhere.
You have one?
Yeah.
Okay.
Dat valt eigenlijk sinds 2 jaar geleden mee bezig ben.
Ja.
Ook weer computerwerk van opleiding bij vrouwen met heel veel kant.
Ja, 50 mensen.
Ja, ik probeer zo 50-50 te doen, dus ook nog wel experimenteel
Ja.
werk in VG, maar
Ja, dat is niet altijd evident natuurlijk. Hè. Waart je ingelogd? Of?
nee, ik
Was van een ander. Ja, voor een uurtje. Of dat ik niet zo. Voor studiesysteem. Ja. Let's put it away safely. Let's leave that. I'll probably do the administration this afternoon, but in case we get sidetracked. Use. Right. Safely. And this way. Okay, that's done. Right, time is so let's continue. I'll share my screen again. I didn't mute myself, so that's fine. Okay, 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 and go. All right. Maybe one practical thing. So basically, this session is being recorded. If you want access to the recordings, no problem. But I don't publish the recordings. Publish in the sense of making them publicly available in the broad sense, because I do screen recordings, so basically the names of the participants are visible at times, especially the chat, but also the participants list has been recorded at some point, I'm afraid. So I'm not going to make them public in that sense. They will be on YouTube, but as unlisted. So that means you can only find them when you have the link. So if you want access to the recordings, no problem. Just let me know and I'll send you an email with the link. This will take some time because I first need to, well, first Blackboard needs to do its thing so that there actually is a recording which you can download. Then I need to download it. And then I need to upload it to YouTube, and YouTube also has to do its thing because before it is a YouTube video. So it takes a while, but normally I hope it's done by this evening. I have a fast internet connection here, so it should be feasible to do it fast. Okay, so personally I was a little bit disappointed by the performance which we got. Now, if you think about it a little bit, then actually we had 4,096. Well, no, we didn't explicitly say that, but we had many threads. We don't know how Vectorize is going to do its magic, so we don't know how many blocks there were. We don't know how many threads per block it choose, but we can safely assume, and that will be the case, that there were very many threads, and each thread actually didn't do much work. Each thread actually just computed the result for one random number, for one complex number. Okay, so the amount of work per thread was pretty low. The number of threads is pretty high, which means that the overhead is going to be pretty huge. Because, yeah, there can be that many threads, but they need to be managed. They need to be created. They need to be destroyed, etc., etc. All that takes time. So having many threads is a very positive thing on GPUs, but they should have enough work to do. And that is one of the reasons why things went, well, why things were disappointing here, because by our naive approach, just say, okay, do your thing, and one thread is doing one iteration, well, one complex number. It means that at some point, not necessarily all at the same time, but there were 100 million threads. One per Z value. We had 10,000 times 10,000 of such, so that's 100 million. So basically that means 100 million threads were created, managed, destroyed, before we got our computation. That's a lot of threads. And yes, GPUs are designed to handle many threads. You can happily oversubscribe in the sense that you can have many more threads than you actually have, let's say, compute units. That's no problem. But creating 10 million of them, 100 million of them, wow, I don't know. They need to do some work. And the threads which we created did not have much work to do. So yeah, that means that we have to be a little smarter. So what we need to do is not to go to our matrix of complex values one by one, but in patches, I'd say. So basically you divide your matrix into a number of submatrices, and each thread is going to take care of all the values in that submatrix. So then, of course, you increase by some factor, depending on how large you choose your patches. You increase the work a thread is doing. You decrease the total number of threads you require, and hence you reduce the overhead. Of course, what would not make sense is to have, let's say, in total 4 patches, because then of course you would only have 4 threads on your GPU, and again you would be extremely displeased with the performance. So this is a bit of a balancing exercise. On the one hand, a thread needs enough to do. On the other hand, you also need a sufficient number of threads to keep all your compute units busy. So this is a bit of a balancing act. Okay, so of course, Vectorize is not going to help us here. So what we need is, again, develop our own kernel and use that in order to do this computation. So basically, we want the kernel, so we use the CUDA-JIT decorator. So this is our Mandelbrot kernel. Sorry, it takes our matrix with complex numbers, complex constant, maximum number of steps, and the number of steps which will contain the result. Okay, so now in this case, we are not going to place our computation on a one-dimensional grid, but on a two-dimensional grid. Makes sense, because we are thinking in terms of the complex plane, which is two-dimensional. So Z is two-dimensional, results is two-dimensional. Is it results? No, number of steps is two-dimensional. So basically, let's place our computation on a virtual two-dimensional grid. Okay, so that's why in this case we call the grid function with 2 rather than 1, because that's the number of dimensions of our virtual grid. So for those of you familiar with MPI, this is like a Cartesian topology, so a Cartesian communicator in MPI terms. It's essentially sort of the same reasoning which you do here. Okay, so I mentioned that you can have one-dimensional grids, seen that, two-dimensional grids, three-dimensional grids. That's where it ends. You have four-dimensional grids on a GPU. The reason for that is just historic. It didn't make sense. Why? What do you do on a GPU? Using it to do scientific computations is a fairly newish idea, but at the end of the day, they were intended to do computer graphics. Computer graphics is inherently two-dimensional. And yes, you can do 3D computations for several reasons, for instance, to render multiple frames one after the other, or to do ray tracing, things like that. But basically, that's where it ends. It doesn't make sense in computer graphics to do more than 3 dimensions. And that's essentially where this limitation comes from. Okay, so now we are in 2 dimensions, and we are also going to not only look at the thread ID, but also at the block size. And that's essentially given by the grid size. So again, the argument 2, because we're in 2 dimensions, and that gives us the strides which we want to take. So we'll see later how we get that, but essentially take it as a given here that in our kernel we can get the thread ID and we can get the grid size, the block size. Okay, so now what we're going to do, as you can see, is we're going to iterate starting from X, going to at most the dimension of set in the shape direction, and we do that in steps of stride. X stride, Y stride. So this is of course 2 loops because we're in 2 dimensions. So basically we have 2 indices I and J. Okay. We need to initialize number of steps. We did that before by just setting it to 0. In this case, of course, number of steps is also a 2-dimensional array. So we set it to 0 inside of the for loop. And then we have the same thing as before. We iterate over Z with the same conditions. So basically, nothing fancy is happening here. Okay. Of course, we have to be a little bit careful with the number of steps, that is actually correct. Okay. So something is a little weird here. Several things are weird here. And this can actually not be entirely correct. Okay, I have to check this code because it's at several levels it's incorrect. This initialization doesn't make sense, and here I have ji and here I have ij, so that is not going to make a whole lot of sense. Probably I played with the code a little bit and then forget to restore it completely, something like that, but this is not going to produce the correct results. Anyway, we're concerned with performance in this case, not so much with correctness, but this I need to really revise because that's wrong. Okay. So now, of course, we need less blocks since we will have less threads, since threads are doing more work. So I set the number of blocks still to a respectable value of 512, but that's a factor of 8 less than our original code. So approximately an order of magnitude less blocks. The number of threads per dimension is 16. Okay, so that's per dimension. But now we actually have 2-dimensional blocks. So that means that the number of threads per block is in fact 16 squared. So that's 256. So that's larger than before. We had 128 in the previous example where we had the 1-dimensional array. So now we make that a bit larger. And then, of course, we can compute the number of threads per block as the square of the number of threads per dimension. That's pretty straightforward. Okay. So we need to initialize our data. And in this case, again, we do that in terms of the number of blocks, number of threads per block, in order to make sure that everything fits well into that memory layout. Okay, so this is essentially the same thing as before, different numbers. All right. And so, of course, n is going to be, in this case, 8,192. Okay. Then we create our complex constant. Been there before, know that. Okay, just a second. Yeah, it's not going to happen. Okay. All right. Some people should know better than calling me during working hours, but okay. So basically, we're not going to bother with executing this by transferring data all the time. I mean, been there, done that. Let's not do that again. So we create our data immediately on the device. Okay. We also initialize the result. And in fact, okay, this is a little bit redundant. And again, I shouldn't do that because essentially I'm initializing the result anyway. In the kernel, I set result ij to 0. Here I'm doing it again by creating a NumPy array on the host and setting it to 0 and transferring the whole thing to the device. So that's also not particularly smart, but okay, let's gloss over that. And then again, I'm going to execute my kernel. So again, this Mandelbrot kernel is a sort of function on steroids, and I can configure it. So what I can do is I specify again the number of blocks and the number of threads per block. Okay, so this I specify, and then I use the device version of set and the device version of results to call it. Okay. So the computation is way faster than the visualization in this case. And there is no discernible difference between this plot and the previous one, although there must be differences in this one because there are problems with the implementation. Okay, so let's time this, and that's actually what interests us anyway. And as you can see, it takes 31 milliseconds. And this is a number which you have to compare with something of the order of a second. If memory serves, it was 1 minute 11 seconds, 1.11 seconds, something like that, currently on my CPU. Now it's 31 milliseconds. So basically, here we totally avoid the whole shenanigans of transferring data back and forth. And as you can see, that helps with performance. And secondly, using strides really helps, because we reduced, and that's the most important part here, we reduced the overhead of the individual threads, because now they have way more work. So basically, this is quite a lot more efficient. Okay. So on CPU, we already timed that, I think, but just for comparison. As you can see, now we have a factor of a bit more than 10 difference between our GPU and our CPU. And of course, you can still play a little bit with the number of blocks, with the number of threads per block, with the stride size, etc., etc. Okay. So that's kind of cool. Question is this optimal? Can we still do better? From the next title, section title, you can guess that the answer is yes. But what would be the reason why we might not have optimal performance here? And I'm going to correct the code here, since I'm at it anyway. So this was wrong. Okay. And sorry, I need to, yeah, that's better. And this should be IJ, because otherwise I'm doing very weird things. So let's not. This is not going to influence the performance. This is not even going to visually impact the result. So I'm not going to bother and execute this again, but this code is correct. So let's have a look at it. And what could be an issue here? If you're familiar with optimization for CPU, there should be some red flags here, or one red flag at least.
So you're always looping over the whole length, right? So that's not very optimal in terms of cache misses.
Yeah, indeed. I'm looping over a two-dimensional. Okay, let's rephrase. I'm looping over something that in my head is two-dimensional, a matrix, but which in memory is of course stored linearly as a very long sequence. And then of course the question is, what's the optimal order of my loops? Should I go by row or should I go by column? Okay. Now, there is an interesting difference between CPUs and GPUs. So the question is correct. The question is this loop order optimal? Okay. The answer on CPU is that you should look at the memory layout of two-dimensional arrays. Because what you want on a CPU is maximum memory bandwidth. Your memory bus is pretty narrow. All the transfers of data from RAM to CPU are going to happen on cache lines. That means that if I get a number from memory, say a single precision number, that's 4 bytes. Okay, that's not what's happening. What is actually happening is that you get 64 bytes in total. So somewhere in this array of 64 bytes is the 4 bytes which you want going to be located. But there may be data before it, or there may be data after it, which you're not interested in. But it's going to be transferred anyway, because everything on a GPU happens by cache line. Okay? So that means that if now I do want many numbers, then I need to make sure that my cache line is filled with what interests me in the context of what I'm computing right now. Okay? So that means if my data is stored in memory, in the CPU memory, as row major, so that means the first row of my matrix followed by the second row of my matrix followed by the third row of my matrix and so on, then of course it makes sense to do my iterations row-wise. So basically that the inner loop goes contiguously over what you have in memory. So if you have row major, the outer iteration would be over the rows, the inner iteration over the columns, because then you use your data consecutively as it is stored in memory, same order. And that gives you good performance because you maximize memory bandwidth. Each number in that cache line is going to be used in your computation right now. So that's good. You optimize memory bandwidth and you optimize cache use, because basically these results will be cached and so on. Okay, so that's good. Suppose that your two-dimensional array, your matrix, is stored column-wise. So essentially, we first have the first column, followed by the sequence of the elements of the second column, third column, etc. And I would do the same iteration scheme, so iterating over the rows and then over the columns, then I would be unhappy. Because when a cache line is transferred, I get single precision floating point, 16 floating point values. Okay, but that means that I get the 16, let's say, first row values in the first column. So for 16 rows, consecutive rows, I get the first column. Okay, but if I'm iterating first by row, then by column, then I'm using exactly one of those values, and the other 15 I can't use. So if I have a very long array, a very large two-dimensional array, then of course, by the time I need the element of the second row, that already vanished at least from level 1 cache, probably from level 2 cache. And I need to transfer it again. So that would be very much suboptimal. So that's the situation on CPUs. You have to make sure that consecutive operations operate on data that is close together. Okay? Now, this is actually a little different with GPUs, but it's the same concern. The concern is, how should I access my data? On CPU, it's a little bit different. You actually should make sure that your threads access data that is far apart. So that's essentially the idea. So that means that if we write our kernel, we have to make sure that we actually access it differently. So in this case, what we're going to do is we're going to swap all the indices. You could also swap the for loops, same thing. But here I just swapped the indices. I left the I and the j, but I swapped them in the matrices. And I hope I did it consistently. Let's see. ji, 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 and ji. And again, this one. Why do I do this? Okay, let's going to fix it here. Maybe there's a reason which now at this point in time escapes me why I did it, why I indexed this differently, but I don't see why that would be the case. So I'm going to change it and see whether that works. Okay, so let's run this and time it and see what we get. Okay, so we get 29 milliseconds, and that was originally 31. Yeah, okay. So basically, again, take this with a grain of salt. Normally, the difference should be a bit faster. I'm going to run it again because I get this slowest run thing, so probably my GPU was trying to wake up or something like that. Or transferring data, what do I know? Okay, 7.6 milliseconds rather than, what was it, 31? Yeah, then 31. So you see, by coalescing memory, I actually get a factor of 5 in performance. Everything else remained the same. The only thing I did was access my array in the correct way. Correct way, in the way that gives me the best performance. So the technical terms for this basically is coalescing memory. And that is something that you really should pay attention to, because otherwise, indeed, you lose a significant factor of potential performance. Okay. So these are actually the main concerns when you are doing lower level GPU development. And now that's actually independent of whether you are doing that with Numba, with one of the other frameworks which are available for Python, or whether you are doing that with OpenMP in C, C++, or Fortran, or whether you're doing that in CUDA, or whether you're doing that on HIP, whatever, the principles always apply. You have to make sure that a thread has sufficient work. So typically you do strided access so that a thread does a patch rather than an individual value of your computation. And you have to make sure that you access memory in the correct order. Doing that gives you good performance. Neglecting that gives you way less performance. Remember that where we come from, essentially, again, with this run of benchmarks, but the ratio should be similar. We started with 1 second, a bit more than 1 second on the GPU. So we got a lot better, a factor of 30, I think, when we strided our computation. And again, we got a factor of 5 when we did when we coalesced the memory. So basically, we went from 1 second to 6 milliseconds. So that's a factor of, what is it, 180? No, that's a bit too much. 120 something, whatever, something like that. So that is pretty huge. And of course, that makes a difference between an effective GPU and a GPU which is just slower than your CPU. Okay, there was a question. Let me see. Yeah, so basically what the C versus F does is indeed either row major or Fortran major. So basically that means C is row major, F for Fortran is column major. So yes, that changes things, but of course then you have to mirror that with the access pattern. So yeah, you can do that, but it's the same at the end of the day. At some point you need to be aware of how you access your data. So the C and the F option is also something that works with NumPy. The default is C, so row major, but if that for some reason is useful, you can switch that to Fortran major, to column major, essentially. So maybe a general remark again, and that applies to GPU, CPU, whatever. If you translate an algorithm from, say, language A to language B, then it's of course very important to check how the how arrays are stored in that language. So for instance, by default in C, C++, and Python, so NumPy, arrays are stored row-wise. In R, Fortran, Julia, MATLAB, they're stored column-wise by default. So if you take your MATLAB algorithm, translate it into Python with NumPy, that's something that you need to take into account. So that's also the same here. Suppose you have a textbook and there is a, I don't know, whatever language algorithm listed, and you want to port that to Python using Numba here and writing your own kernels, then take into account that you have to maybe change the order of the for loops, or alternatively the order of the indices. So that's something to be aware of, that makes a difference. So also be very careful when you use just a textbook and it lists pseudocode. Then again, yeah, okay, what is it? Is it row major? Is it column major? And how should your loops be ordered? Okay. And then so one of the things that is useful to know, of course, is how this mapping happens between blocks and these thread coordinates. And this is just a simple way of actually checking this. So the index essentially is the thread index. And if we have a two-dimensional layout of blocks, then we have the grid coordinates. So basically we can write a kernel in order to check that. And then this is what you get. So basically you see that the first thread is going to do, or index 0 is going to be for the first row. So that's always useful to know, and this is how you can check that. So here we have the same thing, but now again, different problem. So essentially we have again an array. We have in this case less blocks. We create some array and we want to compute the sum. Okay, we transfer the thing to the device, and the result is also on the device. It's initialized to 0, and this is going to be my kernel. So basically I'm going to compute the row sum here on that array, and again I'm going basically row-wise here. So when we do that and run the kernel, we can get a result. Notice I'm very explicitly transferring my data here. I do a copy to host, And I think this is synchronized, but to make sure, I'd better add CUDA synchronize, because then I'm really sure that it's synchronized. Okay, and then I get my data. So as you can see, this is my row sum. So if I time that, same computation, but now done multiple times, no data transport. Okay, get 12 microseconds. Same thing, but now column-wise. Now I compute a column sum. Timing it is going to give me 7, well, almost 8 milliseconds. So this is, the column sum is significantly faster. Again, it's all in the axis pattern. So by happy accident, let's put it that way, is the kernel of the column sum using coalesced memory, while the row sum is not. Okay, that's too bad if you need a row sum, of course. Yeah, you have to live with it, but realize that there are differences. That's the main purpose of this illustration. Okay, so let's go one step further. So basically, it's also possible to create functions that are only defined or are available, let's put it that way, that are available on the device. And again, if you know a bit about CUDA, you know that there are host functions, device functions. So this is to define device functions. Those can be called from code on the device, no problem. And in this case, that's easy. We just have CUDA JIT as before, but now we set device to true. So this is going to be a function that we cannot call from our Python code. We can't call this from our notebook. This can only be called from within kernels that run on the GPU. That's basically the idea. In this case, the function is pretty straightforward. It's just computing a distance, or norm if you want. And then basically we get some data. And this is the kernel. And indeed, I can now use the distance device function, which is the device function I just defined. So this is the way to create functions that you can call from kernels on the device, and you don't care about them on the host. So you need to do that because you can't just create a Python function and call that from a kernel. That will not work. So you need to make sure that the code of that function gets translated into CUDA and gets defined on the device. And that's exactly what is happening with this CUDA JIT device is true. Okay, so now you can actually compute the distance, and we get some warning. Okay, it's apparently not happy with the performance for some reason. Host array used, yeah, okay. So I'm using a host array in the CUDA kernel. So NumPy is kind enough to say, okay, are you sure you want to do this? Please transfer that thing to the device before you invoke. So that's basically what this message says. Okay, and basically the result is all right. So I have this testing function which allows me to see whether that's okay. Okay, so that was about it for NumPy, and essentially we covered the essence of computing on a GPU. All the rest is essentially syntax. So if you go to a different framework, you'll encounter the same concepts of a kernel, explicitly or implicitly, the concept of strided access to your data, In other words, make sure that your CUDA threads have enough to do, and also memory access patterns, so try and coalesce memory. And that's essentially what you need to know in order to use a GPU more or less effectively. And as you can see, the difference between naive and knowing what you do can be a factor of 100. Can make the difference between your GPU being rather useless or a lot faster than your CPU. Okay, let's pause here for a second for questions. Are there any questions at this point? Not really, also not online. Okay. So I'm going to save this guy because I did make some changes that I want to keep. All right, and close. Okay. Let me have a look at the time. Okay, there's still an hour left. Let me see which one is interesting. So the Scikit CUDA thing, unfortunately, I don't get to run anymore. So basically, we're not going to do that. That's easy. The reason I actually don't really know, but I think it's a matter of compatibility between, on the one hand, this package, and on the other hand, the CUDA drivers. I don't think it supports the latest drivers or something like that, and I can't get it installed. So yeah, it's just doesn't work on my hardware, and it's very unlikely to work on HPC hardware even as well. So basically, let's forget about that. It's a pity because it was actually nice, but yeah, okay. It's a while ago, as you can see last year, that I checked. So maybe by now there is an update, but okay, I'm not going to bother with that. Okay, let's perhaps have a look at CubePy. Because this looks very much like NumPy. It's actually designed in order to be very NumPy-like. So in that respect, it can be interesting. So let's load all the modules. So there are not many. For some reason, I also import SciPy. Don't remember why, but we'll see. But CubePy as CP, and that's the important thing here. Okay, so I'm going again to create some data. It's going to be two-dimensional, essentially a 2000 by 2000 matrix. And it's just going to be random numbers. It's all going to be NumPy at this point. So basically, that is pretty straightforward. And A and B are both same shape and both have random numbers. Okay. So let's do a matrix multiply, which is fairly straightforward. It's just A and B. So this is NumPy going to do that. And under the hood, it is also, of course, going to do that using whatever BLAS implementation there is in this environment. Most likely it's an open BLAS. It might be Intel MKL, not entirely sure. We could check. Let's perhaps have a look. Always a good thing to do, that you know what is running in your environment. So basically Mamba list. And let's grab for MKL. Probably we won't find anything. No, it's likely open BLAS. So let's see. libBLAS. Yeah, libopenBLAS is the guy which is under the hood. Okay. So, yeah, it's a good implementation, so no problem there. All right. If we time this, you see that it takes approximately 193, 193 milliseconds. Okay, so this timing actually tells you a little bit more. Let me just point it out, because you might not be familiar with that. So something which is interesting is that if you look at the wall time, sorry, I need to look here. If I look at the wall time, I see it's 200 milliseconds, but CPU time, system time, and so on actually adds up to 3 seconds. That's weird, because the wall time is the time I'd see if I check my watch between hitting return and getting the result. So why is the total time a lot larger than the actual wall time? The answer is in how you count. How do you count time? And the way that is used time and the system time is counted. Let's see whether that's the correct answer. Yes, indeed, multi-threading. That's exactly the point. Because all the cores on my CPU, because this is a CPU computation, all the cores on my CPU are going to compute. And what I get with user time and system time, and hence total time, is the time added which all cores spent. Okay, so that's nice because this shows me that in fact under the hood, multiple threads are computing to get my matrix-matrix multiplication done. So although I didn't specify any parallelism here, I mean, I didn't do anything. There is no explicit multi-threading anywhere. So basically I get that for free because I use openBLAS. And openBLAS, if you ask it to do a degen, so a matrix-matrix multiplication, it is going to do that multi-threaded. So that's kind of cute. You get the same thing if you use Intel MKL as your BLAS library. So that's actually a very nice thing. So just as an aside, essentially, you can see whether your code is running in parallel automatically or not. And this even allows me to estimate how efficient this is, because I get, let's take the user time, not the system time. I get 1.2 seconds, and the wall time is 0.2 seconds. So basically that means that I get a factor of 6 in compute time. So this is not brilliant because I already mentioned my CPU has 8 cores. So I would in fact hope that that factor is 8 rather than 6. But again, it's not bad. It's not bad because of 2 reasons. One reason is the trivial one, which I mentioned before, like a million times. Lots of stuff is happening on my CPU, so not all my cores devote all their time to doing the computation I want them to do. So that means that I can't expect a speed up of 8. There is another thing which also happens on this laptop, which would not happen on a compute node, and that is I have 8 physical cores, but hyperthreading is switched on. So essentially that means that 2 threads are executing on the same core simultaneously. Okay, that's great, except that on this particular CPU, And again, that changes with CPU generations. So in the latest one, that's much less true. But for this one, it's still very true. The logic which is required for floating point computations is not doubled in a core. So a core has 2 units that do logical control, basically. It has 2 units for integer computations, but it has only a single unit for floating point computations. So basically that means OpenBLAS will see 16 cores, because if I check the number of cores on this machine, it will tell me that there are 16. Yeah, because of hyperthreading, but that's not going to be effective. These 2 threads on each core are competing for that floating point unit. And hence they actually do only half the work, which they potentially could. So expecting a factor of 16 for numerical intensive computations is not going to happen, because there's only sufficient hardware to do 8 at a time. So that is something that has been improved with later generations of CPUs. This is a Skylake, so that's already Ice Lake, Sapphire Rapids. So 2 generations old, basically. So on Sapphire Rapids, which is the most recent hardware we have in the KU Leuven cluster, this would actually be a little bit different. But okay, it's something that you need to keep in mind if you are benchmarking, especially on multi-threaded applications. Okay. All right. Now, let's see how we can do the same computation, but now on the GPU. So, of course, to be fair, we have to make sure that our data actually is on the GPU. So let's transfer things to the GPU. So basically, we're copying A and B and creating A def and B def. So we also want to time that because it takes time. And as you can see, this is fairly expensive. So the wall time is a 6/10 of a second. So over 600 milliseconds. So if you compare that to the computation time of the multiplication, you're already lost. Because the only thing we've done up to this point is transfer the data from the CPU memory to the GPU memory. We haven't done any computation yet. Okay, so let's do the computation. And then, as you can see, well, it's still a bit disappointing because it's still longer than doing that on CPU. Why? Because there's not enough to do. Multiplying 2 matrices with 4,000 elements, that's not so many computations. That's basically 2,000 times 2,000 times 2,000. So yeah, that is not that much in terms of parallelism which you get on a GPU. So basically, this is not entirely fair yet, but okay. Okay, why am I doing that twice? Something's happening here. Okay, let's do it again. Because that seems to be much faster if I do it a second time, which is a bit weird. Yeah, so this is much faster. Why is this much faster? That's weird. Okay. Yeah, I don't think I'm doing the right thing here. Basically, yeah, wait, QPy. It's lazy. The transfer is lazy. That's the reason. So basically, the data was actually only transferred at the moment when it was required. So that's the difference with QPy. Sorry, got confused a little bit with the NumPy thing, with the numPy thing. But basically here, essentially the data gets transferred when you use it first. So that's why the first execution is significantly slower. The second is significantly faster. So that's the actual compute time. It's only 3 milliseconds. So we can see that if we create the data directly on the device, so now there's no synchronization between host and device, then we do the multiplication and we get the same result. Different matrices, of course, but they have been transferred. Well, they have been created directly on the GPU because I use CP random here. So that gives me immediately device array. Everything is on the device immediately. So basically, you can see that this is significantly faster. So yeah, I had forgotten that if you just copy the data or think you copy the data, that actually it's not really a copy. You create a device array, but the data is not transferred yet until you need it. So it's lazy, and hence if you execute the first time your multiplication, actually your data gets transferred. If you do the second time, the data is there and you immediately have your, well, you don't immediately have your result, computation is still done, but no data transfer happens. Okay. So another example with the matrix power. So again, we create a host array and we do the NP matrix power function. Okay, it takes 2 milliseconds. This is 1000 by 1000 matrix, so a little smaller. We create a device array and the data is initialized on the device immediately. And we get a similar function. So again, also matrix power function, but now in this case, it's the QPy version rather than the NumPy version. I hope this takes a lot longer because it's a lot faster and hence it's repeated many more times because otherwise I'm going to be disappointed here. I think I'm going to be disappointed. Okay, it might be that my GPU is saying enough is enough. Let's redo this. That seems to be a problem. Okay, let's not push things because something is wrong and there's no point in wasting a lot of energy here. Okay, I have to check what's going on here because that is not okay. What might be the problem is that it's a while ago that I updated this environment, and meanwhile, of course, the CUDA drivers changed, probably rather significantly. So that might be that there's a version mismatch between what QPy hopes to find and what's actually there as a driver. Normally, I should have backward compatibility with more recent drivers than the CUDA libraries, but still, I'm afraid that that's the issue. Because also it seems that my fan doesn't spin down, so my GPU is doing stuff, most likely, which I don't really want it to do. Yeah, there's quite a lot of background activity going on. So, and there's a lot of data on the GPU also. Yeah, okay. Don't know. I'm not going to execute this because this is probably also going wrong. But the point is basically that the QPy library has many of the functions which you find in NumPy. It's just a drop-in, and also in SciPy. So in this particular case, the singular value decomposition. Now, one of the things that you may notice that in fact the singular value decomposition on the GPU is slower than on the CPU. A reason for that is that the singular value decomposition is very hard to parallelize. So to do this well is already hard if you do that with OpenMP on a CPU, but it's even harder to properly do on a GPU. So yes, you can do an SVD, and no, maybe it's not the best idea. But that depends on the algorithm. So it's not necessarily true that each and every algorithm can be implemented efficiently on a GPU. And singular value decomposition is notoriously hard to parallelize, which means that doing that on GPU is going to be a lot more difficult even than doing that on CPU. So it's always a matter of checking what is the most efficient. Now, again, it depends. If your data is already on the GPU, you might not care about this performance difference. Because if you would have to transfer it back to the CPU to do a more efficient SVD there, and transfer the result again to the GPU to continue efficient processes there, then likely it would not weigh up. And it's better to tolerate a not so performant algorithm in order to save you the transfer time. So that's a consideration which you always also have to take into account, of course. Okay, so for instance, if you do the same thing but not with a SVD matrix decomposition, but with a QR decomposition, you see that in fact the GPU is faster. So it depends, in this case, very strongly on the algorithm. Also for SVD, you have to be a bit careful. You have to parallelize in factors of 2, because otherwise it doesn't work optimally. Then you need to do some padding and so on, and that also makes you lose a lot of performance. So this is just to show you, well, okay, there are algorithms which won't run very well on a GPU. Okay, so you need to check. But as you can see, using QPy is quite easy. It's just kind of a drop-in replacement for NumPy/SciPy. Okay. The time is okay. So let's have a brief look at PyCUDA. So PyCUDA is pretty low level, I'd say, but it's interesting for a number of reasons. So one reason is if you want information about your device, PyCUDA allows you to get that very easily. So basically, we are going to do the imports. The import auto init is going to make sure that the GPU is properly initialized in order to run PyCUDA computations. So that's going to happen automatically. And we want to import a driver because that is going to give us information about our GPU. That's the thing which we are going to use to query our GPU. Okay. So as you can see, one of the things that I can ask of the driver is a list of devices and how many I have. So in this particular case, that's not going to be very interesting because I have only one GPU in my system. Yeah, I have two. There's also the discrete GPU on the CPU, but yeah, that doesn't count because this is of course NVIDIA only, and that discrete GPU on the processor is an Intel thing, so they don't talk to one another. Okay, so if I've got the number of my device, I can instantiate a device object, and I can ask information from that. So for instance, I can ask for the name, I can ask for the capabilities, and so on. And that is key value pairs in attributes. So if I execute that, and let me do that because this is actually not this GPU, that's the one which I have in my desktop system. So let me re-execute it for this one. And then you see that the device is indeed an RTX 3060 laptop GPU. You see the device capability, so that's your compute capability. That's 8.6, so that is quite okay. Then lots of parameters. Things you also see here somewhere in this huge mess of data. You see cache size here, so that's also interesting to know. Blah, blah, blah. What I'm trying to spot, which I don't find. And this is interesting. The block dimensions and the so the maximum block dimensions. This is interesting because you see that there is an asymmetry here. So in the X and Y direction, it's 1024. In the Z direction, it's only 64. Again, historic reasons. This will differ from GPU to GPU, but in this particular case, yeah, this is a gaming GPU. So why would I care about a very large Z dimension? I'm mostly interested in getting stuff on my screen, and the Z dimension I only need for rendering multiple frames simultaneously. So there is a maximum to what you want from a gaming GPU. So basically that's why this limitation is there. Okay, you have the maximum grid dimensions and so on. Again, note the symmetry, the lack of symmetry rather. But what I'm trying to find, multiprocessor count. So this is the number of streaming multiprocessors on this device. So that would of course be different on a GPU. Okay, let's not go there. So basically with PyCUDA, you have similar capabilities. You can instantiate data on your GPU, transfer data from the GPU to the CPU, etc., etc. So let's not go there. That's just the same thing, different syntax. And then you can define kernels. So with NUMA, we define kernels just by annotating our function with CUDA-JIT. And then we had access to, on the one hand, the grid, the index, and the grid size. So here, actually, there are a number of kernels, but you have to specify those explicitly. And the point is that what you are in fact specifying is C code, or rather CUDA directly. So essentially, we have an element-wise kernel. So that would do the same thing as NUMBA vectorize. But here, in this particular case, we have to do that more explicitly. So basically, we have to specify what goes in and out. So, well, not what goes in and out, but basically this is the first string is the declaration of the parameters of my function, of my kernel. So in this case, I have two floating point pointers going in, and I'm going to do a computation using the value of in to initialize the corresponding value in out. That's basically the idea. So if you know C, and even if you just know Python, you see that something is odd here. In and out are defined. That's no problem. They will be floating point numbers. But what about I? There is no I here, defined anywhere. So that's one of the features of PyCUDA. If you write such an element-wise kernel, the I will be an element of your input and output. That's essentially the idea. So the I is the index. And the last argument is essentially the name you want to give the kernel. So this is fairly low level in the sense that the code which is here is in fact CUDA, or C if you want, or C++. But to use this, you really need to know C. Okay. Basically, we transfer data, we test this. So this is another example, but now with a kernel that it's a bit more sophisticated, it takes additional arguments. So it's still analyzed, as you can see, and X, Y, and R are going to be arrays. So that's our data, which we process element-wise, and alpha is going to be a constant. Again, the I is defined automatically, and we can use X and Y in order to compute R, each time the corresponding element. So that's your typical SAXP kernel, which you use often in benchmarks. In benchmarks for streaming memory. Okay. So yeah, that's a little more annoying than Numba, of course. So this is yet another example of an element-wise kernel, and this is again our example of the Julia set, or the Mandelbrot set, whatever you want to call it. So you recognize the code is the exact same thing, only I've been lazy here, and I'm using the apps function in order to do the comparison for the norm of the complex number. So don't directly compare performance results you get from this with Numba results for two reasons. This one should be a bit slower because I use the ops function, which does a square root under the hood. And the other reason is there is an error in the Mandelbrot code for Numba because I compare with 2 where I should compare with 4. And that, of course, influences the number of iterations I'm doing, and hence it will not be the same. I have to still correct this in the Numba notebook. Okay, but apart from that, you see that again the same thing happens. We have that magic index I, which is plugged into the code for us, or rather, the strings you specify will be plugged into a template, which is a C function, or rather a CUDA function, and which defines your kernel. So that's how this works. Okay, same plot. So one of the things is an element-wise kernel, but what you also very often do is a reduction. So you do an element-wise computation, but then you aggregate the results into one number or an array of numbers. And PyCUDA helps you doing that easily using a reduction kernel. So basically, you need to specify more things. You need to specify the type of the result. You need to specify the neutral element of that reduction. So for some that would be 0, for a product that would be 1, for, I don't know, you would have to have the neutral element of your operation. Then, how do you do the reduction? So that could be a sum, that could be a product, whatever, but that needs to correspond. And then the mapping of the types and basically the argument string. So here is an example. So this is our type. The neutral element is 0. The reduction expression, let me reformat this a little bit so that you can actually see it, is a plus b. So that means you need to look up in the documentation which is which in case you have a reduction operator which is not commutative, because then a and b play a different role. Now, I don't know that many meaningful reduction operators where it matters, but okay. At any rate, you would need to know. Okay, then the map expression. So basically, that is what is going to happen to element-wise, hence the index I again. And then the arguments. So we get 2 vectors in, and then the name of the kernel. So that would be your typical reduction kernel. And again, the values, the string values that you specify here are flushed into a template that gives you a complete CUDA function. That's essentially the idea. And again, same thing. And then the most general one is just a source module. And what you see here is just plain CUDA. It will compile it and it will run it. But of course, that implies that you actually need to know CUDA. And you already recognize one of the things that I mentioned. So this is a device function. So that's essentially my kernel, which I'm going to launch. And apart from that, are there any other interesting things to notice? Oh yeah, I've got some constants here, but yeah, that's not particularly interesting. Okay. So essentially this is just a long string, nothing more. I also have a global function. This essentially is going to help me to actually launch my kernel. So there's on the one hand a device function, on the other hand a global kernel function, and this I can call from my actual CUDA code, my C++ CUDA code, which executes on the device. So you create the kernel based on the source code, and you have to say, okay, which function do I actually want? Since this is a function that will launch the kernel, it must be a global function, and hence it's the polykernel, which is the global one here. Okay. And then we can execute this. Again, we have to set the block size and so on, as usual. But that's basically how that works. So if you're familiar with CUDA, and you want to use CUDA from Python, then PyCUDA is definitely not a bad approach. It is going to use templating essentially in order to, well, templating in the sense that filling out a template, not in the C++ sense of the word, to generate CUDA code, compile it, and so on. And that's basically the idea. The point is you need to know CUDA, otherwise this is fairly useless. Okay. QPy with it. Courant just shows we use random numbers in the context of PyCUDA. So let's not go there. Numba read it. Question in the chat. Okay, let me close this guy and let's go to the chat. LTO meaning link time optimization. Is that the acronym you mean? So let me try to interpret your question correctly. So if I get it correctly, and you actually have a CUDA source file, and you would compile that into, let's say, a shared object, do you need to use link time optimization? I'd say that yes, I would use that, because if you're lucky, the CUDA compiler will actually do link time optimization, in the sense that things that it could try and do is to for instance, it will have more information about inlining at that point. So that is something it could do if the inlining code is in a separate CU file. So yeah, it would make sense to do that, I think. How much you will gain is a different matter. That depends on the complexity of your code, but that might definitely help. So anything the compiler sees, it can optimize. The compiler sees only one CUDA file at a time. So basically what link time optimization at the end of the day does is it has more information, because it has not only individual CUDA files, but it has the object code generated from all the CUDA files. And hence it has more information, and hence can try to do some optimizations. To be honest, how far that goes in CUDA space, I can't tell you. I don't know. But it won't hurt to switch it on. It will increase your link times potentially considerably. So I would say benchmark. If you don't care about your link times, yeah, do whatever. If link times go significantly up and you're developing, then maybe it's worth to benchmark and to see whether the link time optimization actually gives you a performance edge. So yeah, again, the answer depends on what you're doing exactly. But that's at the end of the day what link time optimization does, regardless of whether that's on GPU, CPU, wherever. It exploits more global information than your compiler has access to. That's essentially the idea. So yeah, it can help or not. Okay. Each time you see slow timing, on the examples you're running from this repository or in general? Because that's not clear from the sentence. So in general, when you're benchmarking, the thing, of course, is that you should benchmark what interests you. So one of the things that's dangerous if you are doing CUDA benchmarks, and actually doing any benchmarks, is micro benchmarking. With micro benchmarking, I mean source file, and I try to compile. Okay, so basically we're talking general CUDA here. We have a .cu file, you compile it, you run it, etc., etc. So in that case, it's indeed the what you get is the total execution time. Now, the total execution time is of course determined by a number of things, by what happens on your CPU. That's one thing. Then on data transfers between host and device and vice versa, and by the time it takes to execute your kernels on the GPU. So that's the sum of the things that can happen and that will contribute to your benchmark results. So what you need to be careful when you're benchmarking is that the ratio between all these things is representative for your final application. What do I mean by that? If you start off by a small computation and it's only a part of a much larger application and you start to optimize that, then of course the risk is that the majority of your time is actually spent in transferring data, and of course that remains significant, but in the overall picture of your application that might disappear if the compute load is going up. So if you add an additional kernel that operates on that same data and that doesn't require any transfers because your data is already on the device, so basically it might be that at the end of the day it turns out that the execution of your kernel is quite fast enough and that it seemed pretty slow because of the ratio between data transfer and compute. So if you add more kernels that operate on data that's already on the device that don't need to transfer data, that ratio changes. And it might be that at the end of the day, your data transfer is insignificant with respect to your computation. So that's the thing. You have to be careful not to micro-benchmark. That's essentially what you need to be careful of. What you can do is run a profiler. So basically, if you have your CUDA code, NVIDIA provides a profiler, which will give you more detailed information about how your time is spent transferring data, running your kernel, when your kernel starts to execute with respect to your data transfer, etc., etc. So it can give you a timeline resolution of the different event streams that go to your GPU. So that is a better way of looking at things, profiling, rather than just timing. And of course, that again is absolutely not specific to GPUs. That's at the end of the day what you always should do, run a profiler and see where your time is going, rather than just get a very broad picture of, okay, this took 10 seconds. Yeah, that's nice, but where were they spent? You can't know unless you profile. You can do that using a profiler, that's the easiest way. Or you can say, okay, I'm going to surround my individual function calls by calls to timing, etc., etc. You can do that. If you do that, however, in the context of GPUs, GPU programming, remember that things are asynchronous. So basically, the fact that the call to your kernel, launching the kernel, ends, does that not mean that the execution of your kernel is done? So that's something to keep in mind, because that's what you need to exploit if you want to overlap computations on host and on device, or data movement and computations. So basically, that's what you need to take into account there. Okay. But that is, of course, pretty specific. And that is actually general GPU, well, okay, that's programming CUDA. or OpenMP or whatever, rather than doing that in Python. Okay, let me perhaps conclude by talking a little bit about Rapids, because that's a little bit of a different take on problems. So the thing we have been doing now is using GPUs and actually programming them in large part. So basically what we did was writing our own kernels up to some extent. But of course, one reason to use GPUs might be that you use pandas. You have very large data frames, you have complicated operations. Question is, can you speed them up on GPUs? The answer is yes. And actually, there should be two answers, of which I only checked one, because I only recently learned that there is another option which I need to explore, but I really didn't have the time. I was preparing for another training. But the answer that's true for a couple of years is yes, you can speed that up by using Rapids. And Rapids is a NVIDIA thing. So they have taken pandas, or the ideas of pandas, and kind of re-implemented that in order to run efficiently on GPUs. So that's at the end of the day what Rapids is. You can install Rapids on your own computer, no problem. But let me perhaps quickly show you. So this is our Open On Demand server. And now probably I'll need to log in or not. Let's see. No, the central login seems to do its thing. That's good. Okay. So normally there should be Rapids somewhere. Yeah, NVIDIA Rapids. So basically, I'm not going to do it because probably I won't get a job running anytime soon, given the current load on GPUs. But that will launch a notebook, and that notebook will have Rapids pre-installed. If you run that on a GPU node, then of course you can use this easily. You can also do it yourself, no problem. So I have Rapids installed on my laptop. Normally that should still function. And then basically what you can use is QDF. And that's of course CUDA data frame. Okay. So essentially what Rapids tries to do is a drop-in replacement for pandas. That's the idea behind it. Okay, so this doesn't work. What's going on? No module name pandas. Yeah, right. Okay, that's kind of easy to fix. Panda install pandas. Okay. I should have that cached, so essentially this should be really, really fast. The emphasis being on should be. Okay, the answer is no. I need to, no, I don't need to download it. Okay, anyway, go. Okay. All right, and all right. Okay, so now that should work, hopefully. Cross my fingers hope to die. Okay, yeah, right, no. No QDF, that's interesting. Okay, let's have a look. Rapids. Either I have a special environment for this, yes, or I ran the whole thing in a container, because somewhere I have a Rapids container. But there is an environment here. Now the question is, does that actually exist on my system? That is something completely different. So let's Mamba deactivate. Okay. Yeah. It was printed. Okay, so it's there. That's good. Then number activate. And what was the thing called? Rabbits. Okay. Yeah, let me just to make sure. Copy paste this. All right, then rabbits. Where are you? You are nowhere on the system. Yeah, most likely that thing lives on my desktop computer, not on my laptop. Okay, let's do mamba env create -f environment. Okay, I might try this because I have to now download quite a lot of stuff. So this might not, okay, great. Looking for. Okay, so this is old and it's not going to, okay, I need to, yeah, so likely this is too old. I'll update it. I'm not going to start changing my environment because I could do that pretty easily, but let's not go there. Because also the Rapids download is going to be unpleasant. It needs to download CUDA libraries and so on. I know that they are large, so this would take more time than I actually am willing to spend on this. But let's just go through the notebook because normally the numbers are there. So again, I would get slightly different numbers due to load of my CPU and my GPU, but okay. So basically, I'm going to create a data frame. This is a pandas data frame. So essentially, it has 20,000 rows and it's random data. So 20 million rows, so it has random data. Okay. So creating a QDF, so a CUDA data frame is as easy. Just the same thing, only you call the corresponding constructor from QDF. Okay, so if you look at the data, then you see that by default, for the pandas data frame, you've got float 64. That's indeed what you would expect. So there's no surprise here. And similar for the GPU. Also, the size is exactly the same. So no surprises there. Okay. So now the question is, if we compute the column mean of A, how much time does it take pandas? How much time does it take the CUDA data frame? And as you can see, the difference is quite significant. It takes 38 milliseconds to do it on the GPU, on the CPU. It takes 2 milliseconds to do it on the GPU. So that's a speed up of, well, almost 10. Okay, that's kind of nice. So other operations, for instance, if I do the mean again, but now not column-wise, but row-wise. Axis is 1, so that means I'm doing it row-wise. So I'm generating a lot more data here. Then you see that on the CPU it takes 870 milliseconds. On the CPU it takes 40 milliseconds. So approximately a factor of 20. A little bit more. And this is an old version of Pandas, by the way, because of course we're already at Pandas 2.1. something if memory serves. So yeah, this is a fairly old version of Pandas. So I should redo these benchmarks with a up-to-date Pandas version, because now I'm comparing apples to oranges, not really fair. But anyway, you see that it makes sense to use Pandas on the GPU using Rapids. Or does it? Again, it depends on what you're doing. If you're doing this interactively, for data exploration, I really don't care whether my operation takes 38 milliseconds or 2 milliseconds. I'm not going to notice. The rate at which I'm typing is so slow that is totally irrelevant. Now, of course, if I make my data frame a lot larger, then perhaps it makes sense. But then the data must fit in the memory of my GPU, because otherwise I don't profit from my GPU. So, yeah, does it make sense? Open question, I don't know. But it works and it's faster. So, of course, if you do lots of operations on a data frame and they take significant time in total, then of course this does make sense. Because then of course that factor of 20 or whatever is really very significant. For just exploring your data, as long as you are, let's say, in the sub-second range of execution times, do you really care? Because most of your time is going to be spent on thinking on what to do, rather than have Rapid doing it for you. So this is quite relative. And also, of course, yeah, it's nice that you get a factor of 20, but you need the GPU. I've got one in my laptop, yay, hooray. But if I need one on the cluster, it needs to be available. If there is no node with a GPU available, Rapid is not going to do anything for me. It won't even run. So basically, what takes longer? Waiting for a node with a GPU so that I can use Rapids, or just live with a execution time which is a little bit longer? Open question. Depends on what you're doing. But it's something to keep in mind, that if you see claims like, okay, it runs 1 million times faster my data frame operations than they run on CPU, yeah, that's nice, but doesn't make sense. Do you get anything out of it? Maybe, maybe not. Okay, so basically there are some other timings here to create new columns and so on, because that might make a difference. But again, this has not executed apparently. Okay, so basically tests with categorical data and so on. So quite a number of, let's say, representative operations, a group by. As you can see, on average, Rapids is faster, but often not that much. Often just a factor of 3. Okay, that is, or that was most likely on this GPU. But yeah, that also means that to gain a factor of 3 in execution speed, that I also used quite a lot more energy, because my GPU is consuming quite a lot of memory, quite a lot of energy. So is that factor of 3 really worth it? I don't know. Again, it depends on your use case. In interactive use, no, because even on this data frame with 20 million rows, I never go up to half a second. Okay, I almost go up to to a second in some operations, but in most I don't. Okay, suppose 1 billion rows. Probably I'm not going to be able to store it in memory anyway, not even on my host memory. So yeah, where is the advantage of things like Rapids running on GPU? It's unclear in a way. So it exists. It may be useful for very specific use cases, but in general, it may not be such an interesting thing. The alternative, which I mentioned, which I just heard of, so if you're into data science and into pandas, I don't need to tell you that Polars is the new kid on the block, that it is faster than pandas, and that it actually does multi-threading on your CPU. Apparently, it also runs on GPUs, I didn't test that. I don't know anything about performance. It's something that is on my to-do list to improve this particular training. But I heard of it like, I don't know, 14 days ago, and I was busy preparing a training I gave last week. So essentially, I didn't get around to test that out. But it's something to keep an eye on. But of course, for polars, it will be the exact same story as for rapids. Is it going to benefit you at the end of the day? I don't know. Even if you look at the performance of polars just on the CPU, you get maybe a speed up of a factor of 3. Yeah, that's great, except if you consider that Pandas is using a single core on my CPU, Polars is using 16, well, okay, 8, all 8 of the physical cores, and it only gives me a factor of 3. I'm somewhat unimpressed, because that's a parallel efficiency of less than 50%. It's not something to write home about. It's not something to be impressed by. So all things are very relative, as usual. Okay, time to conclude. Are there any questions? If not, we end here for today. I hope it was somewhat useful. Few of the next trainings coming up. Machine learning with Python is one of the first ones after the holiday recess. And another one, which is interesting if you're interested in HPC in general, is code optimization. That's mainly about how hardware influences the performance of your code and how you can program in order to exploit that hardware rather than hope that magic will happen and that your code runs efficiently. So that's probably the things that are scheduled for January. Next week, we will have a meeting in which we will fix the schedule for the second semester. There will be quite a lot on C++, on parallel programming with OpenMP and MPI, software engineering, and so on. So you can find the details probably after the holiday season on the VSC website. Okay, that was it. So thanks for joining, and yeah, maybe see you in another training or somewhere else in HPC, country, land, whatever. Yep, see you.